If you could shrink yourself down to the microscopic level and float through the cosmos, you'd see something incredible. Tiny particles of dust drifting through the darkness, spreading like cosmic breadcrumbs across the universe. This dust isn't ordinary, it's ancient, older than Earth itself, and it holds the secrets to how planets, stars, and even life itself came to be. But where does it come from? Where does it go? And could it be the key to understanding the origins of everything around us? This is the story of cosmic dust, one of the universe's smallest yet most powerful forces, shaping the cosmos in ways we're only just beginning to understand. Let's start with the basics. When we think of dust, we imagine the kind that gathers under our furniture or floats in the sunlight coming through a window. But cosmic dust is nothing like that. These are microscopic grains made of carbon, silicon, ice, and metals, formed in the most extreme places in the universe. Some of these dust particles have traveled for billions of years, surviving violent explosions, intense radiation, and the freezing cold of deep space. They're survivors, carrying the chemical fingerprints of their origins across the cosmos. But how does cosmic dust even form? The story begins in the hearts of dying stars. When a massive star reaches the end of its life, it doesn't just fade away, it explodes in a supernova, sending a shockwave of energy across space. In that explosion, heavy elements like carbon, oxygen, and silicon fuse together, creating tiny solid particles. These grains are microscopic, just a few nanometers across, but in the vacuum of space, they can travel vast distances. Some are blown away at incredible speeds, escaping into the interstellar medium, the vast space between stars, while others remain trapped in the remnants of their parent star. Over time, these dust grains begin to clump together, forming larger particles. Some of them mix with gases, forming vast clouds of dust and gas called nebulae. These nebulae are some of the most beautiful objects in the universe, massive, glowing clouds that stretch for light years. They may look peaceful from a distance, but inside, a chaotic process is taking place. Gravity pulls dust and gas together, creating dense regions that, over millions of years, collapse under their own weight to form new stars. This is where things get interesting. That same dust that was once scattered by a dying star now becomes part of the birth of a new one. It's a cycle that has repeated since the beginning of time. Stars die, they spread their elements into space, and those elements become the building blocks for the next generation of stars and planets. In a way, cosmic dust is like the ashes of the past, carrying the legacy of long-dead stars and giving birth to something new. But the journey of cosmic dust doesn't end there. Some of these particles travel much farther, drifting through space for millions or even billions of years. They move through the vast, empty stretches between galaxies, sometimes getting caught in the pull of a new solar system. When a young solar system forms, dust plays a crucial role. It clumps together to form asteroids, comets, and eventually planets. In fact, Earth itself was built from cosmic dust, tiny particles that stuck together over millions of years, growing into the planet we live on today. And it doesn't stop there. Even after planets form, cosmic dust continues to play a role. Every day, Earth is bombarded by tiny dust particles from space, some as small as a grain of sand, others much larger. These particles burn up in the atmosphere, creating meteors, or shooting stars, that streak across the night sky. But some of this dust makes it to the surface, carrying with it clues about the history of our solar system. Scientists have even found microscopic dust grains on Earth that are older than the Sun itself, tiny time capsules that give us a glimpse into the universe's distant past. But cosmic dust isn't just important for planets and stars, it might also be connected to life itself. Some scientists believe that cosmic dust could have played a role in the origin of life on Earth. Certain dust grains contain complex organic molecules, the building blocks of life. These molecules could have hitched a ride on comets or asteroids and been delivered to Earth in its early years, helping to kickstart the chemical reactions that led to life. If that's true, then the story of life isn't just a story about Earth, it's a story written in the dust of the cosmos. And here's where things get even more mind-blowing. Cosmic dust doesn't just shape the universe, it affects how we see it. When light from distant stars and galaxies travels through space, it has to pass through clouds of dust. This dust can absorb and scatter light, making some objects appear dimmer or even invisible. Astronomers have to account for this when studying the universe. If they don't, they might misinterpret what they're seeing. In fact, some of the biggest mysteries in astronomy, like dark matter and the expansion of the universe, could be influenced by the effects of cosmic dust in ways we don't fully understand yet. So, what does all this mean? It means that cosmic dust isn't just space debris. It's one of the most important ingredients in the universe. It's responsible for building planets, forming stars, shaping galaxies, and possibly even creating life. It's a cycle that never ends. Dust is created, it travels, it clumps together, and it starts the process all over again. It's a reminder that nothing in the universe is ever truly lost. Everything, even the tiniest specks of dust, has a role to play. And perhaps the most incredible part? We're still learning about it. Scientists are sending missions to space to study cosmic dust up close, collecting samples from asteroids and comets to analyze what they're made of. The more we learn, the more we realize just how connected everything is, how the dust from ancient stars helped create the world around us, and how the dust floating through space today might one day form new worlds. Think about that the next time you see a shooting star. That streak of light might just be a tiny piece of cosmic dust, burning up as it enters Earth's atmosphere. But before it got here, it traveled across the universe, carrying the echoes of long-dead stars, the whispers of galaxies, and maybe, just maybe, the story of life itself. Cosmic dust is more than just a passive traveler in space. It actively interacts with its surroundings in ways that shape entire solar systems. Some of these interactions are violent, while others are slow and subtle, playing out over millions or even billions of years. And yet, despite its small size, this dust can influence everything from the formation of new planets to the very way we observe the universe itself. One of the most fascinating aspects of cosmic dust is how it changes as it moves through space. When a dust grain is first ejected from a dying star, it carries the unique chemical signature of that star. But as it drifts through space, it undergoes a series of transformations. It collides with other particles, it gets bombarded by cosmic radiation, and it interacts with the interstellar medium, the thin gas that fills the space between stars. These interactions can alter its structure, sometimes breaking it apart, other times helping it grow by collecting more material. One of the most important places where dust plays a role is in protoplanetary disks, the swirling clouds of dust and gas that surround young stars. These disks are the birthplaces of planets, and cosmic dust is the raw material from which they form. At first, the dust grains are tiny, barely larger than molecules. But over time, they stick together, forming larger and larger clumps. Some of these clumps grow into pebbles, then into rocks, and eventually into planetesimals, massive objects that can be hundreds of kilometers wide. This process isn't easy. Space is vast, and the chances of two dust grains colliding and sticking together are incredibly low. But certain forces help speed up the process. One of the most important is turbulence. Within a protoplanetary disk, gas and dust swirl around chaotically, creating eddies and currents that can push particles together. This turbulence increases the chances of dust grains sticking to each other, eventually leading to the formation of planets. But dust doesn't just help create planets, it also influences the way those planets evolve. In the early days of a solar system, dust clouds can block sunlight, affecting the temperature of young planets. Some planets may end up too hot or too cold depending on how much dust surrounds them. In some cases, dust can even help form atmospheres. When dust particles collide with a planet's surface, they can release trapped gases, contributing to the formation of an atmosphere. One of the biggest mysteries in astronomy is how dust affects the habitability of planets. Scientists have found that certain types of cosmic dust contain complex organic molecules, the same kinds of molecules that are essential for life. These molecules can survive the harsh conditions of space, and if they land on a young planet, they could help jumpstart the process of life. This raises an incredible possibility. Could cosmic dust be responsible for spreading the building blocks of life across the universe? This idea, known as panspermia, suggests that life didn't necessarily originate on Earth. It could have come from space. If cosmic dust can carry organic molecules across the cosmos, then life as we know it might have started on a distant planet, only to be transported here by dust, asteroids, or comets. It's a mind-blowing concept that challenges everything we think we know about our origins. But cosmic dust doesn't just play a role in planet formation and life, it also affects entire galaxies. Dust is one of the key components of the interstellar medium, influencing the way galaxies evolve over time. When a galaxy forms, massive clouds of dust and gas come together under the force of gravity. Over time, these clouds collapse, forming new stars and planets. But as these stars age and die, they release more dust back into space, continuing the cycle. The amount of dust in a galaxy can tell us a lot about its history. Young galaxies, which are still actively forming stars, tend to have a lot of dust. Older galaxies, on the other hand, have less dust because much of it has already been used up in the formation of planets and stars. By studying the dust content of different galaxies, astronomers can piece together their life stories, learning how they formed and how they've changed over billions of years. But dust also presents a challenge for astronomers. Because it absorbs and scatters light, it can make certain objects in space difficult to see. Some of the most distant galaxies in the universe are hidden behind thick clouds of dust, making them nearly invisible to optical telescopes. This is why astronomers use infrared telescopes. Infrared light can penetrate dust clouds, allowing us to see objects that would otherwise be hidden. One of the most famous examples of this is the James Webb Space Telescope. Unlike the Hubble Space Telescope, which primarily observes visible light, James Webb is designed to study the universe in infrared. This allows it to peer through dust clouds and reveal details about star-forming regions, distant galaxies, and even planets orbiting other stars. Thanks to this telescope, we're seeing the universe in a whole new way, uncovering details that were once completely hidden from view. But cosmic dust isn't just something that astronomers study from afar. We can actually collect and analyze it right here on Earth. Scientists have found cosmic dust particles in some of the most unexpected places, including deep-sea sediments and Antarctic ice. These tiny grains have traveled across the cosmos, surviving the journey through Earth's atmosphere to land on our planet's surface. By studying them, scientists can learn about the history of our solar system, the composition of distant stars, and even the origins of life. Perhaps one of the most exciting discoveries in recent years is that of interstellar dust grains that come from outside our solar system. These grains are incredibly rare, but they provide a unique glimpse into the wider universe. Unlike dust that originates from our own sun, interstellar dust carries the chemical signatures of other stars, allowing scientists to study the processes happening in distant parts of the galaxy. And this is just the beginning. In the coming years, new missions will be launched to study cosmic dust in even greater detail. Scientists are developing spacecraft designed to capture dust particles from comets, asteroids, and even interstellar space. These missions could reveal new insights into the history of our solar system, the formation of planets, and the fundamental processes that shape the universe. Cosmic dust is a reminder that the universe is constantly changing, constantly evolving. Every grain of dust has a story to tell, a story that began in the heart of a dying star, traveled across the cosmos, and eventually became part of something new. Some of this dust has ended up on planets, some of it has become part of new stars, and some of it has even found its way to Earth. And perhaps, just perhaps, some of that dust contains the very ingredients that made life possible. If that's true, then our story isn't just the story of Earth, it's the story of the universe itself, written in dust and scattered across the cosmos. Cosmic dust is one of the most fundamental yet mysterious components of the universe. It exists everywhere, from the cold voids of interstellar space to the fiery atmospheres of newborn stars. And despite its tiny size, often smaller than a grain of sand, its influence spans entire galaxies. But the real question is, what happens to dust over time? How does it evolve? And what role does it continue to play as the universe ages? One of the most fascinating aspects of cosmic dust is how it changes as it moves through different environments. When a dust grain is first ejected from a star, it is largely composed of the elements that were forged inside that star, things like carbon, silicon, and iron. But as it drifts through space, it encounters high-energy radiation, charged particles, and magnetic fields that alter its structure. Some grains get shattered into smaller pieces, while others grow as they collect additional material. This constant transformation means that cosmic dust is never static, it's always evolving. Some of the most dramatic changes happen when dust encounters a supernova explosion. Supernovae are some of the most violent events in the universe, releasing vast amounts of energy in a matter of seconds. When a dust cloud is caught in the blast of a supernova, it gets exposed to extreme temperatures and high-energy radiation. Some of the dust is completely destroyed, vaporized into individual atoms. But other grains manage to survive, altered by the intense conditions. These surviving grains carry the chemical fingerprints of the supernova itself, acting as cosmic messengers that tell the story of the explosion. But dust doesn't just endure supernovae, it also plays a role in forming new stars. When a dense cloud of gas and dust collapses under the force of gravity, it forms what's known as a protostar, a young star that hasn't yet begun nuclear fusion. Dust helps regulate the temperature of these forming stars by absorbing and re-radiating heat. Without dust, star formation might look very different, or perhaps wouldn't happen at all in the way we know it. And then there's the connection between dust and planetary systems. Over millions of years, dust grains in a protoplanetary disk gradually stick together, forming pebbles, then rocks, and eventually full-sized planets. But even after planets form, dust continues to shape their evolution. It can influence their atmospheres, change their climates, and even contribute to geological processes. For example, Earth is constantly bombarded by tiny dust particles from space. Most of these particles burn up in the atmosphere, creating meteors, those bright streaks of light we see in the night sky. But some particles make it all the way to the surface, adding trace amounts of cosmic material to our planet. Over billions of years, this steady influx of dust has slightly altered the composition of Earth's surface. But perhaps the most intriguing question is whether cosmic dust has played a role in the origin of life itself. Scientists have discovered that some cosmic dust grains contain complex organic molecules, the same kinds of molecules that are found in living organisms. These molecules form naturally in space, created by chemical reactions on the surfaces of dust grains. If dust carrying these molecules landed on a young planet, it could have helped kickstart the formation of life. This raises another question: could cosmic dust be responsible for spreading life throughout the universe? The idea, known as panspermia, suggests that life's building blocks may have traveled from planet to planet, or even from star system to star system, hitching a ride on dust grains or meteorites. If this is true, then life on Earth may not have originated here. It may have come from somewhere else entirely. But cosmic dust isn't just a passive traveler. It also interacts with planetary atmospheres in complex ways. On Earth, for example, dust from space can influence weather patterns. When dust particles enter the upper atmosphere, they can act as nucleation sites for water vapor, helping to form clouds. Some researchers believe that changes in the amount of cosmic dust reaching Earth could even influence long-term climate cycles. And Earth isn't the only planet affected by cosmic dust. On Mars, dust storms can engulf the entire planet, lasting for weeks or even months. Some of this dust comes from the Martian surface, but some of it may also originate from space. If cosmic dust is continually adding material to Mars, it could be influencing the planet's chemistry in ways we don't fully understand. In the outer solar system, cosmic dust takes on an even more mysterious role. Around Saturn, for example, dust from space interacts with the planet's rings, adding new material and slowly altering their structure. Some of Saturn's moons, like Enceladus, even produce their own dust by ejecting ice particles into space. These icy grains mix with dust from interstellar space, creating a complex and ever-changing environment. And beyond our solar system, dust continues to shape the universe on the grandest scales. In distant galaxies, vast clouds of dust obscure our view, making it difficult to see what's happening inside. But these dust clouds aren't just obstacles, they are also the birthplaces of new stars and planets. Without dust, galaxies wouldn't be able to form new generations of stars, and the universe would be a much darker, emptier place. Perhaps one of the greatest mysteries of cosmic dust is how it influences the universe's overall structure. Some researchers believe that dust plays a role in the distribution of dark matter, the invisible substance that makes up most of the universe's mass. While dark matter itself doesn't interact with light, dust does. If dust is more concentrated in certain regions, it could affect how we perceive the distribution of dark matter, leading to new insights about the fundamental nature of the cosmos. In recent years, astronomers have started using cosmic dust as a tool for studying the universe's history. By analyzing the composition of dust grains, scientists can learn about the conditions that existed billions of years ago, when the first stars and galaxies were forming. Some of the dust we observe today is incredibly old, older than our solar system, older than our galaxy, perhaps even older than the Milky Way itself. And as our technology improves, we're finding new ways to study cosmic dust in greater detail. Missions like the James Webb Space Telescope are providing unprecedented views of dusty regions of space, revealing structures and processes that were previously hidden. Meanwhile, space probes are collecting dust samples directly from comets and asteroids, allowing scientists to analyze them in laboratories here on Earth. But despite all we've learned, many questions remain. What exactly determines the lifespan of a dust grain? How does dust interact with black holes? Could dust grains be carrying signs of alien life? These are questions that scientists are still working to answer, and every new discovery brings us one step closer to understanding the full story of cosmic dust. One thing is certain, dust is far more than just an afterthought in the universe. It is a fundamental building block of planets, stars, and even life itself. Every grain of dust carries a history that stretches back billions of years, shaped by the forces of gravity, radiation, and time. It is a silent witness to the universe's most dramatic events, from the birth of stars to the death of galaxies. And as we continue to explore the cosmos, we are beginning to realize just how much of our own story is written in dust. Whether it's the dust that formed our planet, the dust that shaped our atmosphere, or the dust that might have carried the ingredients for life itself, one thing is clear: cosmic dust is not just a byproduct of the universe. It is one of the universe's most essential ingredients. Cosmic dust, despite being microscopic, holds the power to shape the cosmos in ways that challenge our understanding of the universe. It plays a role in the formation of stars, fuels planetary evolution, and even has implications for the very fabric of space-time itself. But the journey of cosmic dust does not end with its formation. It is part of an endless cycle, continuously being created, transformed, and recycled across billions of years. When we examine cosmic dust more closely, we find that its composition is as diverse as its origins. Depending on where it forms, dust can be made of silicates, carbon-rich compounds, ice, or even exotic minerals that do not naturally exist on Earth. Some dust grains contain traces of heavy elements like gold and platinum, materials that were forged in cataclysmic stellar explosions. In a way, every dust particle carries a cosmic fingerprint, a record of its past that tells the story of where it has been and what forces have shaped it. One of the most intriguing mysteries about cosmic dust is how it interacts with the electromagnetic spectrum. Unlike planets or stars, dust does not emit its own light. Instead, it absorbs and scatters light from surrounding sources. This means that in some regions of space, dust acts as a veil, hiding what lies beyond. But in other cases, it acts like a lens, bending and distorting light in ways that can reveal hidden structures in the cosmos. This effect is especially important in the study of distant galaxies. Many of the oldest and most distant galaxies in the universe are obscured by thick clouds of dust. Without the ability to peer through these dusty regions, astronomers would struggle to understand how galaxies evolve over time. Fortunately, by using infrared telescopes like the James Webb Space Telescope, scientists can see beyond the dust, revealing stars and planetary systems in their earliest stages of development. The presence of cosmic dust also raises important questions about the origins of planetary systems. When a new star forms, it is surrounded by a swirling disk of gas and dust. Over time, this material begins to stick together, forming larger and larger clumps. But how does this process actually work? How do tiny dust particles overcome their natural tendency to bounce off one another and instead form planets? Scientists believe that electrical charges may play a key role. Dust grains that collide at low speeds can develop weak electrostatic forces, allowing them to clump together rather than break apart. Over time, these clumps grow into larger bodies, eventually forming asteroids, moons, and even planets. Without dust, the universe would have no planets, no moons, and possibly no life. But cosmic dust does not just shape planets, it also has a profound impact on the atmospheres of worlds across the cosmos. On Earth, tiny particles of dust from space constantly enter the atmosphere, where they interact with water vapor, potentially influencing cloud formation and weather patterns. Some researchers have even suggested that variations in the amount of cosmic dust reaching Earth could play a role in climate cycles, affecting global temperatures over thousands or even millions of years. Beyond our planet, cosmic dust creates breathtaking phenomena. Saturn's iconic rings, for example, are not just made of large chunks of ice and rock, they also contain fine dust grains that scatter sunlight, creating their luminous appearance. The faint halos of dust around Jupiter and Uranus suggest that dust is constantly being created and redistributed by collisions between moons and other small bodies. And then there is the interstellar medium, the vast ocean of gas and dust that fills the space between stars. Though it may seem empty to the naked eye, this region of space is actually teeming with microscopic particles. Some of these dust grains travel incredible distances, carried by interstellar winds or gravitational interactions with passing stars. In some cases, dust that originated in one galaxy may even find its way into another, slowly drifting across the void over billions of years. But what happens when cosmic dust reaches the edge of a black hole? Scientists are still unraveling the mysteries of how dust behaves in such extreme environments. In the accretion disk surrounding supermassive black holes, dust is subjected to immense gravitational forces, heating up to extreme temperatures and emitting powerful radiation. Some of this dust eventually spirals inward, disappearing beyond the event horizon. But some of it is ejected outward at incredible speeds, forming massive jets of material that stretch across intergalactic space. Understanding how cosmic dust interacts with black holes is not just an academic exercise. It could help unlock fundamental secrets about the nature of space-time itself. Some theories suggest that dust grains near black holes could be used to test the effects of relativity, shedding light on how gravity behaves in the most extreme conditions. And what about the role of cosmic dust in the search for extraterrestrial life? Scientists have long speculated that dust grains could serve as carriers for the building blocks of life. Some dust particles contain complex organic molecules, compounds that are essential for life as we know it. These molecules form naturally in space, exposed to ultraviolet radiation and cosmic rays. If dust grains carrying these molecules were to land on a planet with the right conditions, they could provide the raw materials needed for life to emerge. This idea leads to one of the most profound questions of all. Could cosmic dust be spreading life throughout the universe? The theory of panspermia suggests that life, or at least the ingredients for life, could travel between planets and star systems, hitching a ride on dust grains, asteroids, or comets. If this is true, then life on Earth may not be unique. It may be part of a vast, interconnected web of life that stretches across the galaxy. But cosmic dust does not just carry organic molecules, it also serves as a record of past cosmic events. By studying the isotopic composition of dust grains, scientists can trace their origins back to specific types of stars. Some grains contain signatures that suggest they came from red giant stars, while others show evidence of having formed in supernova explosions. In rare cases, dust grains have even been linked to neutron star collisions, events that produce some of the heaviest elements in the universe. And then there is the question of how cosmic dust interacts with dark matter. Dark matter is one of the greatest mysteries in modern physics, an invisible substance that makes up most of the universe's mass. While dust and dark matter are fundamentally different, some researchers believe that dust may provide indirect clues about dark matter's distribution. Because dust interacts with light, it can be used to map out hidden structures in space, potentially revealing patterns that align with dark matter's influence. Despite everything we have learned, cosmic dust remains one of the most enigmatic components of the universe. Every new discovery raises new questions. How do different types of dust grains evolve over time? What role does dust play in shaping the structure of galaxies? Could dust grains hold evidence of past life beyond Earth? One thing is clear: the more we study cosmic dust, the more we realize just how essential it is to the universe's story. Every dust grain is a tiny time capsule, a fragment of the cosmos that has traveled through space for millions or even billions of years. It is a reminder that even the smallest things can have an impact on the grandest scales. And so, the cycle continues. Dust forms in the hearts of stars, drifts through the void, participates in the birth of planets and the emergence of life, and eventually returns to the stars once more. It is a never-ending process, one that has been shaping the cosmos since the beginning of time and will continue to do so long after our own sun has burned out. Perhaps the greatest mystery of all is what new secrets cosmic dust will reveal in the future. With every dust grain that falls to Earth, with every sample collected from a distant comet, we come one step closer to understanding our place in the universe. And as we continue to explore, we may one day uncover answers to questions we have not yet even thought to ask. The cosmic dust cycle is more than just a process. It's a story of destruction and rebirth, a tale of particles that have traveled through space for billions of years, shaping everything from the smallest asteroids to the largest galaxies. And while we have uncovered many details about how dust forms, moves, and influences the cosmos, there are still many mysteries left unsolved. One of the biggest questions is how cosmic dust evolves over time. We know that when it forms in the atmospheres of dying stars or in the debris of supernovae, it starts as tiny grains, often less than a micrometer in size. But as these grains travel through interstellar space, they can collide with other particles, be eroded by cosmic radiation, or even merge into larger structures. What determines whether a dust grain survives its journey or is destroyed? Some scientists believe that magnetic fields in space could play a role in protecting dust particles from destruction. When charged particles interact with dust, they can generate weak magnetic fields that help shield the grains from high-energy radiation. If this is true, then cosmic dust may last far longer than we originally thought, surviving for billions of years before being incorporated into new stars and planets. Another mystery is how cosmic dust influences the chemistry of space. Many regions of the universe are filled with cold molecular clouds, dense areas of gas and dust where new stars are born. Within these clouds, dust grains act as tiny chemical laboratories, providing surfaces where complex molecules can form. Some of these molecules include the basic building blocks of life, such as amino acids and sugars. But how do these molecules form in such an extreme environment? Scientists have conducted experiments in space to test these processes. By placing dust-like particles in microgravity and exposing them to conditions similar to those found in interstellar space, researchers have observed that organic molecules can indeed form on dust grains. These findings suggest that the raw materials for life may be far more common in the universe than previously thought. And what about the role of cosmic dust in planetary atmospheres? We often think of dust as something that exists only in deep space, but in reality, dust is constantly falling onto planets, including Earth. Every day, tons of cosmic dust enter our atmosphere, burning up as meteors or settling onto the surface as microscopic particles. Some of this dust comes from comets, while other grains originate from ancient asteroid collisions. But could some of it be carrying messages from other worlds? In recent years, scientists have discovered tiny interstellar dust particles embedded in Antarctic ice and deep-sea sediments. These grains likely traveled from beyond our solar system, providing a rare opportunity to study material from distant stars without leaving Earth. By analyzing these particles, researchers hope to uncover new information about the environments where they formed, shedding light on the conditions that exist in other star systems. There is also the question of how cosmic dust affects the formation of new stars. In theory, dust should play a crucial role in the cooling process that allows gas clouds to collapse and form new stars. When dust absorbs and re-emits radiation, it helps regulate the temperature of star-forming regions. But observations suggest that some star-forming regions are unexpectedly dust-poor. Could there be unknown processes that destroy dust before it has a chance to contribute to star birth? Some scientists have proposed that powerful stellar winds from newly formed stars may be responsible for clearing out dust from certain regions. If true, this could mean that dust has a much shorter lifespan in active star-forming regions than previously assumed. This, in turn, could affect our understanding of how quickly stars form and how different environments influence their development. And then there is the role of cosmic dust in the grand structure of the universe. When we look at the vast web of galaxies that make up the cosmos, we see intricate patterns of light and dark, structures shaped by gravity, dark matter, and intergalactic gas. But cosmic dust also plays a role in shaping these structures. Some galaxies contain massive amounts of dust, which can obscure entire regions from view. Others appear strangely dust-free, raising questions about where the dust has gone. Recent discoveries have revealed that cosmic dust can even be found in the most unexpected places. For example, astronomers have detected dust in the halos of galaxies, vast regions of space far beyond the visible disks of stars. This raises the possibility that dust is being transported across intergalactic distances, carried by powerful winds or the explosive energy of dying stars. Could this intergalactic dust be influencing the evolution of entire galaxies? Some researchers think so. If dust can travel between galaxies, it might play a role in seeding new star formation in places where it would not otherwise occur. It could also be contributing to the mysterious phenomenon of cosmic recycling, where material from one galaxy eventually ends up in another, blurring the lines between separate stellar systems. One of the most fascinating aspects of cosmic dust is its potential to reveal hidden information about the early universe. Some of the oldest dust grains in the cosmos may still exist today, trapped in the coldest, most remote regions of space. By studying these ancient particles, we could learn more about what the universe was like in its infancy, before the first stars and galaxies had fully formed. In a way, cosmic dust is like a cosmic memory, a record of everything that has ever happened in the universe. Every dust grain has a story to tell, a journey that spans billions of years and countless light-years of distance. And as we continue to explore space, we are only just beginning to unlock the secrets hidden within these tiny, unassuming particles. What new discoveries await us? Will we find evidence that cosmic dust has played a direct role in the origin of life? Could dust grains hold the key to understanding dark matter or even the nature of the universe itself? The more we learn, the more we realize that cosmic dust is not just a passive byproduct of space. It is an active, dynamic force that has shaped the cosmos in ways we are only starting to comprehend. And so, the cycle continues. Dust forms, travels, influences, and is eventually reborn in the next generation of stars. It is a cycle that has been repeating since the beginning of time and will continue long after our own world is gone. Perhaps, in the distant future, the dust that once made up Earth will find its way to a new planet, carrying with it the echoes of everything that came before. The more we study cosmic dust, the more we realize that these tiny grains hold the fingerprints of the universe's greatest mysteries. They are like time capsules, carrying clues about the earliest days of the cosmos, the birth and death of stars, and even the conditions that may have led to life itself. But for all we have learned, there are still countless questions left unanswered. One of the biggest mysteries surrounding cosmic dust is how it interacts with dark matter. We know that dark matter makes up the majority of the universe's mass, yet we can't see it directly. Instead, we detect its presence through its gravitational effects. But could cosmic dust help us unlock the secrets of this invisible substance? Some scientists believe that dust grains may be indirectly influenced by dark matter, moving in patterns that don't match the expected behavior of normal matter. If this is true, then studying the motion of cosmic dust clouds could provide new insights into the nature of dark matter and its role in shaping the universe. Another fascinating puzzle is the connection between cosmic dust and black holes. Supermassive black holes sit at the centers of most galaxies, consuming vast amounts of gas and dust as they grow. But recent observations have shown that some black holes seem to be surrounded by surprisingly large amounts of dust, forming massive, donut-shaped structures called torids. Why does this dust survive so close to such powerful gravitational forces? Some researchers suggest that intense magnetic fields may be helping to keep the dust stable, while others propose that new dust is constantly being replenished by the chaotic interactions of matter near the black hole's event horizon. But the mysteries don't stop there. Some of the oldest cosmic dust in the universe appears to predate the first known stars. This raises a mind-blowing question: where did it come from? The standard model of the universe suggests that before the first stars formed, there should have been no solid matter, only a hot, dense soup of hydrogen and helium gas. Yet some ancient dust grains found in meteorites on Earth appear to be older than our Sun, hinting that solid particles may have existed in ways we don't yet understand. Could there have been an earlier generation of stars that formed and exploded before the ones we know about? Or is there an unknown cosmic process that can create dust without the need for stars? And then there's the question of whether cosmic dust could carry signs of extraterrestrial life. We already know that dust grains can act as chemical factories, forming complex organic molecules. But some scientists speculate that dust could also transport biological material between planets, and even star systems. This idea, known as panspermia, suggests that life may not have originated on Earth but was instead delivered by cosmic dust, meteors, or comets. If true, this would mean that life in the universe could be far more widespread than we ever imagined. To test this theory, researchers have examined dust grains collected from the upper atmosphere, looking for traces of complex organic molecules or even microscopic life forms. While no definitive evidence of extraterrestrial life has been found yet, some unexpected organic compounds have been detected, compounds that closely resemble those found in meteorites and cometary dust. Could these be the remnants of ancient biological processes from beyond our solar system? Another area of study focuses on how cosmic dust might influence the atmospheres of distant exoplanets. When we observe planets orbiting other stars, we often look for signs of atmospheric composition that might indicate habitability. But dust can complicate this process. Some exoplanets appear to have hazy, dust-filled atmospheres that make it difficult to determine what gases are present. In some cases, this dust could be coming from volcanic activity, while in others, it might be leftover material from the planet's formation. Understanding how dust behaves in alien atmospheres could be the key to identifying which exoplanets are truly capable of supporting life. And let's not forget about the role of cosmic dust in shaping the colors of the universe. When we look at distant galaxies, we often see them glowing in shades of red, blue, and gold. But some of these colors aren't just from the stars themselves, they're also influenced by the dust. When light passes through a dust cloud, shorter wavelengths like blue and ultraviolet get scattered, while longer wavelengths like red and infrared pass through more easily. This is why some galaxies appear redder than they actually are. But could dust be affecting our view of the universe in ways we haven't realized? Some researchers think that large-scale dust structures could be distorting our measurements of cosmic expansion, leading to slight errors in our understanding of the universe's age and size. The more we learn about cosmic dust, the more it challenges our understanding of everything from star formation to the fundamental laws of physics. Could dust grains be hiding unknown physical properties? Could they be interacting with forces we haven't discovered yet? The search for answers is far from over. One thing is certain: cosmic dust is not just an afterthought of the universe. It is an essential ingredient in the cosmic recipe, shaping the evolution of galaxies, influencing the birth of planets, and possibly even carrying the seeds of life. Every dust grain that floats through space is part of a vast, interconnected cycle that has been playing out for billions of years, and will continue for billions more. And as we continue to explore the mysteries of the cosmos, one tiny speck at a time, we may one day uncover answers to some of the greatest questions of all. Where did we come from? How did the universe begin? And are we alone? The mysteries of cosmic dust stretch far beyond what we currently understand, and as we continue exploring the universe, we keep uncovering new questions that challenge our fundamental understanding of space and time. These tiny particles may seem insignificant, but they could hold the key to some of the deepest secrets of existence itself. One of the strangest mysteries surrounding cosmic dust is its possible role in influencing the structure of the universe on the largest scales. We tend to think of galaxies as massive, independent islands of stars, gas, and planets, but cosmic dust is present even in the vast spaces between galaxies, drifting in the intergalactic medium. Some scientists believe that this intergalactic dust could be subtly shaping the way light travels across the universe. If dust is more abundant than we currently estimate, it could slightly distort our measurements of cosmic expansion, making it seem like the universe is stretching faster than it really is. This raises an unsettling possibility. What if some of our fundamental assumptions about dark energy, the mysterious force driving the universe's accelerated expansion, are based on an illusion caused by dust? The idea that cosmic dust could be affecting our measurements of the universe's expansion isn't just speculation. Observations of distant supernovae, which scientists use as cosmic mileposts to gauge how space is stretching, sometimes show unexpected dimming effects. Some of this dimming is explained by the natural aging of stars or the presence of gas clouds, but a portion of it remains unexplained. Could there be massive, undiscovered reservoirs of cosmic dust absorbing just enough light to make us think the universe is expanding more quickly than it actually is? If so, we might need to rethink some of our biggest theories about the fate of the cosmos. Beyond its role in shaping the large-scale structure of the universe, cosmic dust may also play a key role in the mysterious cycles of star death and rebirth. When a star dies, it releases enormous amounts of dust into space, enriching the surrounding interstellar medium with heavy elements. But not all of this dust remains in the galaxy. It can be expelled into intergalactic space by powerful stellar explosions or interactions with other galaxies. This means that some of the raw materials needed for star and planet formation are being lost over time. If this process is significant enough, it could affect how galaxies evolve over billions of years. Could the universe eventually reach a point where too much dust has been ejected into intergalactic space, slowing down the formation of new stars? And then there's the question of whether cosmic dust could be acting as a hidden transporter of elements and molecules across galaxies. We know that dust grains can carry organic compounds, the building blocks of life, but could they also be transferring other exotic materials, like superconducting minerals or unknown forms of matter? Some researchers speculate that cosmic dust grains could be carrying atomic structures we've never seen before, exotic forms of carbon, silicon, or even elements that don't naturally occur on Earth. If so, then studying dust grains from deep space could reveal entirely new types of chemistry that don't exist anywhere in our solar system. Another mind-bending possibility is that cosmic dust is interacting with the cosmic microwave background radiation, the faint afterglow of the Big Bang. The cosmic microwave background is one of the most important pieces of evidence we have for the origins of the universe, but some unusual temperature fluctuations have been observed that don't entirely match predictions. Could cosmic dust be scattering this ancient radiation in unexpected ways? If so, it might be subtly altering our understanding of the early universe, making us question key details about how matter and energy first emerged from the chaos of the Big Bang. And what about the role of cosmic dust in planetary atmospheres? We know that Earth regularly encounters tiny dust particles from space, but some planets seem to have much more dust than expected. Titan, Saturn's largest moon, has a thick, hazy atmosphere filled with organic molecules, and some scientists believe cosmic dust could be continuously delivering complex compounds to its surface. If this is true, then Titan might be undergoing chemical processes similar to those that led to life on Earth billions of years ago. Could cosmic dust be a universal catalyst for life, seeding planets across the galaxy with the raw ingredients needed for biology to emerge? Even more bizarrely, some researchers have suggested that cosmic dust could act as a kind of cosmic recording device, preserving the history of the universe in ways we don't yet understand. Dust grains travel for billions of years, accumulating layers of material and interacting with radiation, magnetic fields, and cosmic rays. Each of these interactions leaves tiny imprints on the dust, encoding a record of the conditions they've experienced. If we could learn to read this cosmic memory, we might uncover hidden details about events that occurred long before our solar system even existed. And then there's the question of whether cosmic dust could be involved in strange quantum phenomena. Some physicists have proposed that the smallest dust particles could exhibit quantum behavior, existing in multiple states at once or being entangled over vast distances. If true, then cosmic dust could provide a unique window into the weirdest aspects of quantum mechanics, bridging the gap between the tiny world of particles and the vast scales of galaxies. Could cosmic dust be the missing link between quantum physics and gravity? For now, many of these ideas remain speculative, but as our ability to analyze cosmic dust improves, we may soon uncover answers to some of the biggest questions in physics. Missions like NASA's Stardust probe, which collected samples from a comet's dust cloud, and Japan's Hayabusa missions, which retrieved material from asteroids, have already provided incredible insights into the composition of cosmic dust. But we've only scratched the surface. Future missions could gather dust samples from interstellar space, bringing back material that has never been touched by our solar system. If we can analyze this dust at an atomic level, we might find evidence of unknown elements, new types of molecules, or even hints of extraterrestrial biology. And what if the next big discovery comes not from space missions, but from right here on Earth? Some scientists believe that certain types of cosmic dust settle on our planet in ways we haven't fully accounted for. By carefully analyzing the dust layers and ice cores, deep-sea sediments, and even ancient rocks, we might uncover long-lost records of cosmic events, supernova explosions, galactic collisions, or even past episodes of intense radiation that affected Earth's climate. Could cosmic dust hold clues to past mass extinctions or the origins of life itself? The more we study cosmic dust, the more it challenges everything we think we know about the universe. It is a reminder that even the smallest things can have the biggest impact, and that the secrets of existence may be hiding in the most unexpected places. As we continue exploring the cosmos, one thing is certain: the mysteries of cosmic dust are far from solved. Each new discovery only opens more questions, pushing us further into the unknown. And who knows? Maybe one day, a single grain of cosmic dust will be the key that unlocks the greatest mystery of all: the origin of life, the fate of the universe, or even the nature of reality itself. Cosmic dust is far more than just tiny particles drifting through space. It may be a fundamental ingredient in the evolution of galaxies, the formation of planets, and even the emergence of life. Yet, despite its vast presence, we are only beginning to understand the full extent of its influence. The mysteries surrounding cosmic dust are as deep as the universe itself, challenging our understanding of everything from star formation to the very structure of space-time. One of the most puzzling aspects of cosmic dust is its role in the cooling of interstellar gas clouds. When massive clouds of gas collapse to form new stars, they release enormous amounts of energy. This heat must be radiated away efficiently for the cloud to continue collapsing and forming stars. Scientists have discovered that dust grains act as cooling agents, absorbing heat and re-emitting it as infrared radiation. Without cosmic dust, star formation might take much longer, or might not occur at all. But there's an even bigger mystery. Where did the first cosmic dust grains come from? In the early universe, before the first stars exploded in supernovae, the only elements present in significant amounts were hydrogen and helium. These elements don't form solid dust grains. So how did the first generation of stars manage to form in the first place? Some theories suggest that exotic particles or unknown cooling mechanisms may have played a role, but the exact process remains unclear. Understanding the origins of the first dust grains could unlock secrets about how galaxies formed in the early universe. Beyond helping stars form, cosmic dust might also be responsible for shaping planetary systems in unexpected ways. We typically think of planets forming in protoplanetary disks, giant spinning clouds of gas and dust surrounding newborn stars. Over time, tiny dust grains stick together, forming larger and larger clumps that eventually become asteroids, moons, and planets. But recent discoveries suggest that cosmic dust may also play a role in disrupting planetary systems. Observations of young planetary systems have revealed strange gaps in protoplanetary disks, regions where something appears to be clearing out the dust. One explanation is that young planets are sweeping up the material, but another possibility is that cosmic dust itself is responsible. Charged dust particles can interact with magnetic fields in ways that cause them to clump together or be pushed away, creating unexpected structures in planetary systems. This could mean that dust isn't just a passive ingredient in planet formation, but an active force shaping the architecture of solar systems in ways we don't yet understand. Even in mature planetary systems, cosmic dust continues to play a mysterious role. Every year, Earth collects thousands of tons of cosmic dust, much of it originating from comets and asteroids. Some of these dust grains contain complex organic molecules, leading to speculation that cosmic dust could have delivered the building blocks of life to early Earth. But if dust can transport organic molecules across space, could it also carry other, even more exotic materials? Some researchers have proposed that cosmic dust could be carrying microscopic life forms, or at least the precursors to life, between planets and even between star systems. This idea, known as panspermia, suggests that life might not have originated on Earth at all but was instead seeded by cosmic dust traveling through space. If true, then the discovery of extraterrestrial life might not require traveling to distant exoplanets. It might already be present in the cosmic dust raining down on Earth. But the mysteries don't stop there. Some of the strangest properties of cosmic dust are related to its interactions with radiation and magnetic fields. Dust grains are often electrically charged due to interactions with cosmic rays, and these charged grains can be influenced by interstellar magnetic fields in ways that we don't fully understand. In some cases, dust grains appear to be spinning at incredible speeds, possibly due to tiny impacts from other particles or interactions with radiation pressure. Some scientists believe that understanding how cosmic dust interacts with magnetic fields could provide new insights into the structure of the Milky Way and other galaxies. There's also the question of how cosmic dust affects our view of the universe. Astronomers rely on light from distant stars and galaxies to study the cosmos, but dust can absorb and scatter light in complex ways, distorting our measurements. Some of the strangest optical illusions in astronomy, such as ghostly rings around distant stars or dark patches in otherwise bright nebulae, are caused by cosmic dust. Could it be possible that some of the most puzzling observations in astrophysics, including unexplained dimming of distant objects or strange variations in cosmic microwave background radiation, are actually caused by dust in ways we don't yet understand? Another mind-bending idea is that cosmic dust could be interacting with dark matter. Dark matter makes up most of the mass in the universe, but it doesn't emit or absorb light, making it almost impossible to detect directly. Some theories suggest that cosmic dust could act as a kind of bridge between normal matter and dark matter, helping us uncover the properties of this invisible substance. If dust grains interact with dark matter in even a subtle way, they could provide clues about its true nature. But the most mysterious aspect of cosmic dust may be its ability to store information. Every dust grain that travels through space is exposed to radiation, collisions, and magnetic fields. Over time, these interactions leave tiny imprints on the grain's structure, almost like a cosmic fingerprint. If we could learn to read these imprints, we might be able to reconstruct the history of cosmic events in ways we've never imagined. Could cosmic dust be the key to unlocking a hidden record of the universe's past? The more we learn about cosmic dust, the more questions arise. How much of the universe's history is encoded in these tiny grains? Could dust be shaping planetary systems in ways we don't yet realize? Is it possible that cosmic dust is carrying life across the cosmos, or even interacting with forces like dark matter? One thing is certain. The mysteries of cosmic dust are far from being solved. Every new discovery only deepens our sense of wonder, reminding us that even the smallest things in the universe can hold the biggest secrets. And as our technology improves, we may finally be on the verge of uncovering the hidden stories carried by these tiny travelers of the cosmos. Cosmic dust, despite its minuscule size, is a powerhouse of hidden knowledge. These tiny particles are spread across galaxies, drifting in interstellar space, accumulating on planetary surfaces, and even influencing the very structure of the cosmos. Scientists once viewed cosmic dust as little more than an astronomical nuisance, something that simply obscured distant stars and made observations more difficult. But as our understanding has deepened, so has the realization that cosmic dust may be one of the most important yet mysterious substances in the universe. One of the biggest puzzles surrounding cosmic dust is how it manages to survive the extreme conditions of space. Dust grains are constantly bombarded by high-energy radiation, cosmic rays, and charged particles from stars, yet they persist for millions, or even billions, of years. How do these delicate structures endure such a hostile environment? Some researchers believe that cosmic dust grains may have self-healing properties, allowing them to reform or repair themselves after being damaged. Others suggest that dust grains could be coated in layers of carbon or ice that act as protective shields, preventing them from being completely destroyed. Even more fascinating is the idea that cosmic dust might not only survive in space but actually evolve over time. In the vast, cold stretches of interstellar space, dust grains are exposed to ultraviolet light from distant stars, triggering chemical reactions on their surfaces. These reactions can create complex organic molecules, some of the very same molecules found in living organisms. If cosmic dust is capable of producing and carrying these molecules across the universe, then it could be playing a far more active role in the development of life than we ever imagined. This leads to one of the most intriguing possibilities. Could cosmic dust be responsible for seeding life on Earth and beyond? The theory of panspermia suggests that life's building blocks, or even primitive life forms, could travel between planets and star systems embedded in cosmic dust grains. This isn't just science fiction. Experiments have shown that some microorganisms can survive the harsh conditions of space, at least for a limited time. If bacteria, spores, or other microscopic life forms were shielded within dust grains, they might endure the long journey between planets or even across interstellar distances. But cosmic dust isn't just a potential carrier of life, it also plays a fundamental role in shaping planetary atmospheres. Every day, Earth is bombarded with cosmic dust particles, most of which burn up upon entry into the atmosphere, creating the faint glow of meteors. However, these particles leave behind tiny traces of metal atoms, which can interact with the atmosphere in unexpected ways. Some researchers believe that cosmic dust influences cloud formation, affects ozone chemistry, and even alters weather patterns on a planetary scale. And then there's the role of cosmic dust in the formation of planetary rings. Saturn's stunning rings, for example, are composed of countless particles of ice and rock, many of which are continuously replenished by cosmic dust from passing comets. Similar processes may be shaping the rings of other gas giants, and perhaps even planets beyond our solar system. Some exoplanets are surrounded by dusty disks that could be the remnants of ancient collisions, the signatures of unseen moons, or something even more mysterious. Yet despite all these discoveries, there are still fundamental questions we haven't answered. How much cosmic dust exists in the universe? Is there an upper limit to how much dust a galaxy can produce? Could dust even affect the ultimate fate of the universe itself? Some theories propose that cosmic dust may play a role in dark energy, the mysterious force driving the accelerated expansion of the universe. If dust interacts with radiation or gravity in unexpected ways, it could have consequences for our entire understanding of cosmology. And perhaps the biggest mystery of all is whether cosmic dust is truly unique to our universe. If alternate dimensions or parallel universes exist, could they have their own versions of cosmic dust? Could dust be the key to detecting hidden realities beyond our own? Some physicists speculate that certain anomalies in cosmic background radiation could be explained by interactions between our universe and others, and cosmic dust might be part of the puzzle. Every step we take in studying cosmic dust opens new doors to deeper, more perplexing questions. It's a substance that seems almost insignificant, yet holds the potential to reshape our understanding of space, time, and life itself. The mysteries of cosmic dust are far from solved, and the more we uncover, the more it seems that these tiny particles may be among the greatest enigmas of the cosmos. The study of cosmic dust isn't just a matter of observing particles in the vast emptiness of space. It's about piecing together a cosmic puzzle, one where each tiny speck could unlock a new understanding of how galaxies, stars, and even life itself have come to be. Dust grains are the silent travelers of the universe, moving across billions of light years and accumulating in places that, at first glance, seem far too hostile for anything to survive. Yet, these grains are not only surviving, they are thriving, playing a role in shaping the destiny of the very cosmos we observe. It's hard to overstate how important these dust grains are to the structure of our universe. As we learn more, one thing becomes clear: they are not mere debris scattered throughout space. They are active players in some of the most profound processes in astrophysics. For example, dust plays a critical role in the cooling of gas clouds in interstellar space. When these clouds of gas collapse under their own gravity, forming the stars of tomorrow, dust grains help regulate the temperature by absorbing heat and re-emitting it in infrared wavelengths. Without dust, star formation would be an inefficient and perhaps impossible process. The cooling mechanism that dust provides allows gas to condense, triggering nuclear fusion in the heart of newly formed stars. But the relationship between dust and stars doesn't end there. Stars are the creators of the very elements that form dust. When a star reaches the end of its life and explodes as a supernova, it scatters a wealth of elements, some of which will go on to form the dust grains that populate the interstellar medium. These dust grains are then carried into the cold depths of space, where they accumulate in nebulae, eventually forming the next generation of stars. This cycle of death and rebirth, stars giving birth to dust, which in turn creates the building blocks for new stars, is one of the most beautiful and mysterious processes in the universe. As these grains drift through space, they encounter environments far different from those near their stellar birthplace. Dust grains in the interstellar medium are subjected to radiation from distant stars, high-energy cosmic rays, and violent shockwaves from supernovae. These conditions slowly alter the composition and structure of the dust, transforming it over millions of years. Some grains are shattered, some are chemically altered, and others may even be propelled to new parts of the galaxy by powerful magnetic fields or the force of stellar winds. It's this constant transformation that makes dust so intriguing to astrophysicists. It's not a static material, but a dynamic substance, constantly evolving and reshaping itself in response to the forces around it. And then there's the idea that cosmic dust may not just be a byproduct of stellar life cycles but a direct contributor to the formation of new life. We already know that organic molecules, such as amino acids, have been found in meteorites and cosmic dust grains that have landed on Earth. These molecules are the very building blocks of life, leading to the tantalizing possibility that the essential components for life may have been delivered from space. Could cosmic dust be more than just a carrier of chemical elements? Could it be a conduit for the essential components that spark the creation of life itself? This idea doesn't just have implications for the origins of life on Earth. It could change our approach to the search for life elsewhere in the universe. If cosmic dust could seed life, then perhaps life is not a rare occurrence confined to one planet. Maybe life has been seeded throughout the cosmos, carried on dust grains drifting between the stars. It could be waiting for the right conditions to sprout, ready to bloom on distant worlds that we have yet to even discover. This radically shifts our perspective on astrobiology, suggesting that the universe may be far more biologically connected than we once thought. Of course, cosmic dust also plays a pivotal role in the formation of planets. As tiny dust grains collide and stick together, they form larger and larger bodies, eventually building up to form the planets we know today. This process occurs in the dusty disks around young stars, where the pressure from the gas in the disk and the pull of gravity cause dust to clump together. Over millions of years, these clumps grow into planetesimals, small, rocky bodies that can further accumulate material to form full-fledged planets. But this process isn't just passive, it's also driven by the complex interplay between dust and radiation. Radiation pressure from a star can push on the dust grains, causing them to scatter and spread out across the disk. This pressure is balanced by the gravitational pull of the forming planets, which work to draw the dust in. It's a delicate dance, one that scientists are only beginning to understand fully. The way dust grains respond to this delicate balance could have a significant impact on the overall structure of the planetary system, how far the planets form from the star, whether they grow large enough to become gas giants, and how the presence of dust influences the formation of moons and rings. In the case of exoplanets, planets outside our solar system, the role of dust is even more intriguing. Many exoplanets are found in dusty environments, often within the same protoplanetary disks that give rise to stars. By studying the dust in these disks, scientists can learn more about the conditions that lead to planet formation. Some exoplanetary systems appear to have more dust than others, suggesting that the rate of planet formation in these systems might be higher. In fact, by studying cosmic dust and the way it behaves around young stars, astronomers can start to piece together the conditions that make a planet habitable. They might even be able to use cosmic dust as a marker for the presence of life. But the importance of cosmic dust doesn't end with planets and life. Dust also plays a significant role in the way we observe the universe. The light from distant stars and galaxies can be absorbed, scattered, and even redshifted by cosmic dust in the interstellar medium. This means that our observations of the cosmos are often distorted by the very dust that is shaping the universe. While this can complicate measurements, it also provides valuable information. By studying how light interacts with dust, we can learn more about the composition and structure of the galaxies and nebulae through which that light passes. In a way, cosmic dust acts as a cosmic lens, allowing us to peer into the inner workings of the universe in ways that would be impossible otherwise. Moreover, cosmic dust is an essential ingredient in the formation of stellar nebulae, the birthplaces of stars. When clouds of gas and dust collapse under their own gravity, they form dense regions where stars are born. These nebulae are not only fascinating to study because they are the nurseries of new stars, but they also provide clues about the conditions that were present in the early universe. The dust in these nebulae can tell us about the chemical composition of the gas that was present during the birth of the first stars, giving us a snapshot of the conditions that led to the formation of the first galaxies. Dust grains in these nebulae also interact with the radiation from the newly formed stars, shaping the surrounding environment. They absorb high-energy light from the stars and remit it as infrared radiation, helping to cool the surrounding gas and making it easier for the gas to collapse and form new stars. This cooling process is critical to the formation of the next generation of stars and planets, continuing the cycle that has been ongoing since the birth of the universe. As we continue exploring the mysteries of cosmic dust, it's crucial to understand the complexity of its composition. The grains themselves are not all the same. They come in various forms and sizes, each with distinct properties. Most cosmic dust grains are made of silicate minerals, carbon-based compounds, and metals like iron, magnesium, and aluminum. These materials are the building blocks that make up planets, stars, and even the very elements that comprise life as we know it. The size of these grains can vary, with the majority of cosmic dust particles being only a few micrometers in diameter. While they may appear insignificant when viewed individually, their collective impact on the cosmos is immense. Imagine billions of these tiny particles drifting through space, shaping galaxies, and facilitating the birth of stars and planets. In fact, the size of the dust grains plays a crucial role in their behavior. Larger grains tend to settle quickly under the influence of gravity, whereas smaller grains are more easily carried by radiation pressure or interstellar winds, spreading throughout the galaxy and participating in the ongoing cycle of cosmic material exchange. Moreover, dust grains are not static objects. They undergo a range of physical processes as they travel through space. For example, when these particles encounter intense radiation from stars or supernovae, they can be heated to high temperatures, causing their chemical composition to change. This process, known as thermal processing, can alter the types of minerals that make up the dust grains, potentially influencing the conditions of star and planet formation in the regions where these grains accumulate. But it's not just radiation that affects dust grains. In the cold depths of space, where temperatures can drop to nearly absolute zero, dust can interact with cosmic rays, high-energy particles from distant supernovae and other cosmic events. These cosmic rays can bombard the dust grains, causing chemical reactions that might lead to the formation of new compounds. This process, known as cosmic ray irradiation, is another way in which the composition of dust can evolve over time, influencing the overall chemistry of interstellar space. The interaction between cosmic dust and the interstellar medium, the vast expanse of gas and plasma that fills space, is also of great importance. The interstellar medium is not a uniform environment. It is made up of regions of gas and dust with varying densities, temperatures, and compositions. Dust grains play a crucial role in shaping the properties of this medium. They help to regulate the temperature of the gas by absorbing and re-emitting radiation. This process is especially important in the regions of space where stars are born, as it allows the surrounding gas to cool and condense, enabling the formation of new stars. Furthermore, the interplay between dust and magnetic fields in the interstellar medium is another fascinating aspect of the cosmic dust cycle. Magnetic fields permeate much of space, and they can have a significant impact on the movement and behavior of dust grains. In certain regions of space, dust grains can align themselves with the magnetic field lines, affecting their motion and influencing the overall dynamics of the interstellar medium. This interaction between dust and magnetic fields is a key factor in determining the distribution of dust across the galaxy, and can also play a role in the formation of complex structures like spiral galaxies and nebulae. In some cases, dust grains can even act as catalysts for the formation of new molecules. In the cold, dense regions of space, where temperatures can fall to hundreds of degrees below freezing, dust grains provide a surface on which chemical reactions can take place. For example, molecules like hydrogen can combine on the surface of dust grains to form more complex molecules like water and methane. These reactions, known as surface chemistry, are crucial for the formation of molecules that might eventually play a role in the development of life. But what about the ultimate fate of cosmic dust? What happens to it once it has traveled across the galaxy and participated in the processes of star and planet formation? The answer to this question is tied to the life cycles of stars themselves. As stars age and exhaust their fuel, they begin to expand and shed material into space. In the case of massive stars, this material is often expelled in violent supernova explosions, scattering vast amounts of dust and gas across the galaxy. This material then enriches the interstellar medium, providing the raw ingredients for the next generation of stars, planets, and even life. The process of stellar death and the subsequent release of dust and gas is a critical part of the cosmic dust cycle. It's a never-ending cycle of birth, death, and rebirth, with dust serving as both the progenitor and the product of stellar evolution. The materials expelled by dying stars can eventually form new dust grains, which are then carried throughout space to participate in the formation of new stars and planets. This cycle has been ongoing for billions of years, shaping the structure of our galaxy and ensuring that the raw materials for life continue to be distributed across the cosmos. In some cases, dust grains can even become incorporated into the formation of black holes. These enigmatic objects, formed from the collapse of massive stars, are known for their ability to pull in matter from their surroundings. As dust and gas are drawn into a black hole's event horizon, they are compressed and heated to extreme temperatures, contributing to the black hole's growth. This process of accretion, the gradual accumulation of matter, plays a key role in the formation and growth of black holes, making dust an integral part of the life cycle of these mysterious objects. The influence of cosmic dust extends far beyond just the formation of stars and planets. Dust also plays a key role in the structure and behavior of galaxies themselves. In the spiral arms of galaxies, dust accumulates in vast clouds, helping to regulate the rate of star formation. In the dense centers of galaxies, where supermassive black holes reside, dust can interact with the intense radiation emitted by the black hole, influencing the dynamics of the surrounding region. In fact, the study of cosmic dust can provide valuable insights into the behavior of galaxies, allowing astronomers to learn more about their formation, evolution, and the processes that govern their structure. But the influence of cosmic dust is not limited to just our galaxy. Dust can also travel across vast distances, moving from one galaxy to another. This intergalactic dust plays a role in the overall evolution of the universe, influencing the rate of star formation in distant galaxies and even contributing to the distribution of elements across the cosmos. In fact, the study of cosmic dust can reveal much about the history and future of the universe itself. By analyzing the composition and distribution of dust across different galaxies, scientists can learn more about the processes that have shaped the cosmos and gain insights into the future of our own galaxy. As we continue to study cosmic dust, new discoveries are being made all the time. With the help of advanced telescopes and other instruments, scientists are able to observe the behavior of dust in unprecedented detail. The study of cosmic dust is opening up new avenues of research in astrophysics, cosmology, and even astrobiology. Who knows what mysteries lie ahead as we continue to explore the role of dust in shaping the universe. As our understanding of cosmic dust deepens, we are starting to uncover its intricate connections to some of the universe's most profound phenomena. For instance, dust is not just a passive participant in the grand cosmic cycle, but an active ingredient in the chemical evolution of galaxies. It plays a crucial role in facilitating the formation of complex molecules, particularly in the early stages of star and planet formation. When we peer into the birthplaces of new stars, vast nebulae filled with swirling clouds of gas and dust, we can see how dust grains provide the building blocks for the formation of molecules that are essential for the creation of life. One of the most fascinating aspects of cosmic dust is its ability to serve as a catalyst for chemical reactions. In the cold, dense regions of space, dust grains provide a surface on which simple molecules, like hydrogen, can come together and form more complex compounds. This process, known as surface catalysis, can produce a wide range of molecules, including some that are essential for life, such as water, ammonia, and methane. These molecules are the very building blocks of the organic chemistry that forms the foundation for life as we know it. The interaction between dust and gas also leads to the formation of the first solid objects in the universe, planetesimals. These are small, rocky bodies that can eventually collide and merge to form planets. Dust grains are the first seeds of these planetesimals, coming together through the force of gravity to form larger and larger aggregates. Over time, these planetesimals can accrete more material, eventually becoming planets, moons, and other solid bodies. This process is fundamental to the formation of planetary systems, including our own. However, the role of cosmic dust is not limited to just the formation of stars and planets. Dust also plays a significant part in the evolution of galaxies themselves. As stars form and die, they release vast amounts of dust and gas into the interstellar medium. This material enriches the galactic environment, providing the raw materials for the next generation of stars and planetary systems. The ongoing cycle of star birth and death ensures that dust continues to be recycled throughout the galaxy, fueling the formation of new generations of stars, planets, and even life. In some cases, the dust released by dying stars can contribute to the formation of black holes. As a star nears the end of its life, it can shed enormous amounts of material, creating a dense, swirling cloud of gas and dust around its core. If the star is massive enough, this material can collapse under its own gravity, forming a black hole. This process is not only a key part of the life cycle of stars but also plays a crucial role in the overall evolution of galaxies. The formation of black holes can have a profound impact on the surrounding environment, influencing the formation of new stars and even affecting the dynamics of entire galaxies. As cosmic dust travels through space, it can also interact with other forms of cosmic material. In particular, it can collide with other dust grains, leading to the creation of even larger particles. This process, known as coagulation, can lead to the formation of complex dust structures that can influence the overall structure of galaxies and even the formation of planetary systems. These interactions are also responsible for the generation of new dust grains, which are then incorporated into the next generation of stars and planets. The movement of cosmic dust is also influenced by the magnetic fields that permeate space. These magnetic fields can affect the motion of dust grains, causing them to align with the magnetic field lines. This interaction can alter the way dust moves through space and can have a significant impact on the dynamics of galaxies and star formation. The magnetic properties of dust can also influence the way it interacts with other forms of cosmic material, such as gas and plasma, leading to complex behaviors that are still not fully understood. Perhaps one of the most exciting aspects of cosmic dust is its potential to provide clues about the origins of life itself. Some scientists believe that the building blocks of life, amino acids, proteins, and other complex molecules, could have originated in the dust clouds that filled the early universe. In fact, certain types of dust grains have been found to contain organic molecules, suggesting that dust may have played a direct role in the chemical processes that led to the formation of life. If this theory is correct, it would mean that the ingredients for life are not just confined to Earth but are scattered throughout the cosmos, waiting to be discovered. As our technology improves, we are able to detect cosmic dust in greater detail. New telescopes and space probes are allowing us to study dust grains in unprecedented detail, revealing their composition, structure, and even the processes that shape their formation. For example, NASA's Stardust mission, which returns samples of comet dust to Earth, has provided scientists with a wealth of information about the composition of dust grains from the early solar system. These samples have given us a glimpse into the processes that led to the formation of the planets and the chemical evolution of our solar system. In addition to studying dust grains from comets and other bodies in the solar system, astronomers are also examining dust in distant galaxies. By analyzing the light that passes through clouds of cosmic dust, scientists can learn about the composition of the dust, the types of stars that are forming in the region, and the overall structure of the galaxy. This research is shedding new light on the processes that govern the formation and evolution of galaxies and is providing important clues about the history of the universe itself. One of the most intriguing aspects of cosmic dust is its ability to travel vast distances across space. While most of the dust in the universe is concentrated in the galactic plane, where stars and planets form, there is also dust that exists in the intergalactic medium, the vast, empty space between galaxies. This dust can travel across billions of light years, carried by the expansion of the universe and the movements of galaxies. In some cases, dust grains can even be ejected from one galaxy and travel to another, carrying with them the chemical signatures of their home galaxy. This intergalactic dust can play a role in the formation of stars and planets in distant galaxies, and studying it can help us understand the processes that shape the evolution of the universe as a whole. In the coming years, as we continue to develop more advanced observational tools, we will likely uncover even more secrets about cosmic dust. New telescopes, such as the James Webb Space Telescope, are already providing us with unprecedented views of the universe, including the ability to study dust in distant galaxies in greater detail. With these new capabilities, scientists hope to answer some of the most pressing questions about the role of dust in the cosmos. How does it affect the formation of stars and planets? What role does it play in the chemical evolution of galaxies? And could it hold the key to understanding the origins of life itself? As we venture deeper into the mysteries of cosmic dust, we are learning that its role extends far beyond just the formation of stars and planets. The interactions between dust, gas, and magnetic fields throughout the universe create a complex web of processes that influence the very structure of galaxies, star systems, and even the universe itself. The more we learn about dust, the clearer it becomes that it is not just a passive byproduct of cosmic processes. It is a fundamental component of the universe's ongoing evolution. For instance, in addition to its role in star and planet formation, dust plays an essential part in regulating the temperature and dynamics of galaxies. As dust absorbs and scatters light from stars, it helps to cool the gas in a galaxy. This cooling effect is crucial for the formation of new stars, as it allows the gas to condense and collapse into dense clouds, triggering the birth of new stars. Without the presence of dust to facilitate this cooling process, star formation would be much less efficient, and the rate at which new stars are born would be significantly lower. But dust doesn't just cool gas, it can also heat it. When dust grains absorb ultraviolet light from nearby stars, they remit this energy as infrared radiation. This process warms the surrounding gas, creating a complex feedback loop. As stars form, they heat the dust and gas around them, which in turn can influence the formation of new stars. This dynamic interplay between dust, gas, and star formation is still not fully understood, and researchers are working hard to uncover the intricacies of these processes. Furthermore, dust plays a critical role in the formation of the first galaxies. In the early universe, shortly after the Big Bang, galaxies were formed from clouds of gas and dust. These early galaxies were much smaller and less structured than the ones we observe today, but they were crucial in shaping the larger cosmic structures we see in the present day. The presence of dust in these early galaxies helped to cool the gas and trigger star formation, which in turn led to the formation of more complex structures, such as the first black holes, the first clusters of galaxies, and the large-scale cosmic web. As we study the role of cosmic dust in the formation of galaxies, we are also beginning to unravel the mysterious processes that govern the evolution of galaxy clusters. These clusters, which consist of hundreds or even thousands of galaxies bound together by gravity, are some of the largest structures in the universe. Dust plays an essential role in the evolution of these clusters, as it helps to cool the gas in the intergalactic medium, which can then condense to form new stars and galaxies. Dust is also responsible for scattering light in galaxy clusters, which can have important implications for our understanding of the distribution of matter in the universe. In addition to its role in star and galaxy formation, cosmic dust is also thought to play a significant part in the process of supernova explosions. When massive stars reach the end of their lives, they explode in a dramatic event known as a supernova. These explosions release vast amounts of energy, along with large quantities of heavy elements and dust. The dust created in supernova explosions is then ejected into space, where it can mix with other dust grains, enriching the interstellar medium with new elements and molecules. This dust can eventually be incorporated into new stars, planets, and other celestial objects, continuing the cycle of cosmic evolution. One of the most exciting possibilities that researchers are exploring is the potential for cosmic dust to provide us with clues about the early universe. By studying the composition of dust grains from ancient stars and galaxies, we can gain insights into the conditions that existed in the first few 100 million years after the Big Bang. The dust in these ancient regions may contain traces of the first elements and molecules that formed after the universe's birth. Understanding these early conditions could help us to unlock some of the deepest mysteries of cosmology, including how the first stars and galaxies formed, and what the universe was like during its earliest moments. Moreover, the study of cosmic dust is becoming increasingly important as we continue to search for extraterrestrial life. The presence of organic molecules in cosmic dust raises the intriguing possibility that the building blocks of life could be scattered throughout the universe. Some scientists hypothesize that these molecules could play a role in the origins of life on other planets. If this theory proves correct, it would suggest that life may not be unique to Earth, but rather a common phenomenon in the cosmos. The discovery of organic molecules in the dust surrounding other stars could provide the first direct evidence that life, at least in its most basic form, exists elsewhere in the universe. As we look to the future, the study of cosmic dust is poised to play an even larger role in our understanding of the universe. With the development of new observational tools, such as the James Webb Space Telescope and the Atacama Large Millimeter/Submillimeter Array, ALMA, scientists are now able to study dust in greater detail than ever before. These advanced instruments allow us to observe dust in distant galaxies, measure its composition, and track its movement through space. This data will undoubtedly lead to new discoveries about the role of dust in the formation and evolution of galaxies, stars, and planets. In addition to these tools, upcoming missions to comets and asteroids, such as NASA's OSIRIS-REx and Japan's Hayabusa 2, will provide us with a direct look at the dust and material that make up these small bodies. By studying the composition of these particles, scientists hope to learn more about the early solar system and the processes that led to the formation of Earth and the other planets. These missions could also provide valuable insights into the potential for life elsewhere in the solar system, as many of the molecules found in cosmic dust are also found in comets and asteroids. As our technology continues to advance, we may one day be able to collect samples of cosmic dust from distant regions of the universe. These samples could provide us with direct evidence of the materials that make up other stars, planets, and even alien life forms. The analysis of these dust grains could help answer some of the most fundamental questions in science, including how life began on Earth, whether life exists elsewhere in the universe, and what the ultimate fate of the universe will be. For now, cosmic dust remains a fascinating and mysterious part of the universe, one that holds countless secrets waiting to be uncovered. Whether it's helping to form new stars, enriching the interstellar medium with new elements, or providing the building blocks for life, dust plays a vital role in the cosmic cycle. As we continue to explore the universe and study the properties of cosmic dust, we are sure to learn more about the processes that shape the universe and our place within it. As we venture further into the cosmic dust cycle, we must also consider the environmental impact that dust has within specific regions of space. For example, in the dense molecular clouds where new stars are born, dust plays an even more profound role. These clouds, often referred to as stellar nurseries, are filled with dust and gas that are cooled by the very dust particles within them. This cooling is crucial because it allows the gas to condense into dense clumps, eventually leading to the formation of new stars. Without the presence of dust, the gas would remain too hot to condense, preventing the birth of stars and planets. In these stellar nurseries, the dust doesn't just help with cooling, it also contributes to the creation of complex molecules. As the dust grains collide with one another, they create a surface on which chemical reactions can take place. This process leads to the formation of molecules like water, carbon dioxide, and even more complex organic molecules. These molecules are essential in the formation of stars and planets, as they provide the raw materials needed for future life. It's possible that some of the organic compounds formed on these dust grains could eventually be incorporated into planets, making them potential hosts for life. In regions far from star-forming areas, cosmic dust still plays a critical role in the overall makeup of galaxies. For example, in the outskirts of galaxies or in regions of space between galaxies, dust particles can accumulate, creating dense clouds that can affect the movement of stars and gas. These clouds of dust can act as dust lanes that block the light from stars behind them, creating shadowed areas in space. These dust lanes often serve as important markers for astronomers, as they help outline the structure of galaxies and reveal information about their past. Interestingly, this cosmic dust can even be seen influencing the behavior of galaxies themselves. As dust is scattered throughout a galaxy, it affects the distribution of light and energy within that galaxy. For instance, in some galaxies, the dust can absorb light from stars and re-emit it in the infrared spectrum. This process not only contributes to the overall energy budget of a galaxy, but it can also give astronomers crucial clues about the types of stars and structures present within that galaxy. It's through the study of this dust emission that we can learn more about the formation history of galaxies, their rate of star formation, and their overall evolution over time. As we think about the role of dust within galaxies, we also have to consider its relationship to black holes. In some of the largest galaxies, supermassive black holes reside at their centers, and these black holes can have a dramatic impact on the surrounding dust. As material falls into these black holes, it heats up to extreme temperatures, emitting enormous amounts of radiation. This radiation can affect the dust in the surrounding regions, either by heating it up or by causing it to be expelled from the galaxy altogether. This dynamic interaction between dust and black holes is one of the many mysteries that scientists are working to understand. Beyond the immediate effects of cosmic dust on stars, galaxies, and planets, dust may also have larger-scale implications for the evolution of the universe. Consider, for example, the potential role of dust in the formation of dark matter and dark energy. While we don't yet fully understand the nature of dark matter or dark energy, there are theories that suggest dust might interact with these mysterious substances in ways that we haven't yet discovered. Some scientists speculate that dust could act as a mediator between visible matter and dark matter, potentially helping us to better understand these elusive forces. The fact that cosmic dust is so interconnected with other fundamental elements of the universe, gas, stars, galaxies, black holes, and possibly even dark matter, speaks to its incredible importance. It's like a bridge linking all these components together. In a sense, studying dust allows us to look at the universe as a whole, connecting different phenomena across vast stretches of space and time. Each dust grain has a story to tell, one that spans the beginning of stars, the formation of planets, and possibly even the emergence of life. But cosmic dust doesn't just affect things on a cosmic scale. It has direct consequences here on Earth as well. When dust particles enter Earth's atmosphere, they can affect both the weather and the climate. For instance, dust from nearby comets or asteroid impacts can interact with Earth's atmosphere, sometimes causing changes in temperature, precipitation, and even atmospheric circulation. This can have important effects on weather patterns, as well as on the long-term stability of Earth's climate. Researchers are still studying the effects of cosmic dust on our planet, especially in relation to the history of climate change and Earth's environmental history. In a way, cosmic dust is an eternal cycle, a never-ending dance through the universe that connects the past, present, and future. It is created in the fiery furnaces of stars, travels across vast distances, and participates in the formation of new stars, planets, and even galaxies. It then slowly fades away, being swept up by black holes, swept into the intergalactic void, or incorporated into new celestial bodies. As we continue to investigate the properties and behaviors of cosmic dust, we are also advancing our understanding of the universe itself. Each new discovery about dust opens up new avenues for exploration, helping us to piece together the intricate puzzle of the cosmos. It's not just a question of how dust forms, travels, and contributes to star and planet formation, it's also about understanding the broader implications that cosmic dust has on the fabric of the universe. What role does it play in shaping the galaxies we observe today? How does it impact the formation of the universe's earliest structures? And perhaps most intriguingly, could the study of cosmic dust eventually reveal secrets about the origins of life and the potential for life elsewhere in the universe? In many ways, cosmic dust holds the key to unraveling some of the most profound mysteries of the cosmos. It is a substance that not only shapes the very nature of galaxies, stars, and planets, but it also offers us a window into the origins of life itself. As we continue to study dust, we move closer to understanding not only the evolution of our universe but the possibility of life beyond our own planet. The cosmic dust cycle, from its formation to its eventual return to the void, is an eternal loop of creation and destruction, of building and deconstructing, that reflects the very nature of the universe itself, ever-changing, ever-evolving, and infinitely mysterious. As we dive deeper into the cosmic dust cycle, we can't overlook its long-term implications for the evolution of the universe. Dust is often regarded as one of the universe's most fundamental building blocks. When we observe the vastness of space, we tend to marvel at the stars and galaxies, but it's the seemingly insignificant dust particles that help to shape everything around us. These dust grains, though tiny, play an essential role in the ongoing transformation of the cosmos. One area where cosmic dust is of particular interest is in the study of stellar life cycles. Stars, in their various stages of existence, are responsible for creating and distributing the elements that make up everything we see around us, including planets, moons, and the very bodies we inhabit. The dust produced by these stars plays a crucial role in this process. As a star ages and eventually dies, it expels dust and gas into space, enriching the interstellar medium with the elements needed to create new generations of stars, planets, and potentially even life. Take, for example, the death of massive stars and supernova explosions. These powerful explosions blast heavy elements, such as iron, nickel, and silicon, into the surrounding space, creating large clouds of dust. These supernova remnants then serve as raw materials for the formation of new stars and planetary systems. It is this cycle of life, death, and rebirth that creates the vast array of elements and compounds that make up our universe. Without the dust produced by dying stars, there would be no building blocks for new stars and planets to form. The dust expelled from stars during their death throes can also play an important role in the formation of planetary systems. As these dust particles travel through space, they can collide and stick together, forming larger objects known as planetesimals. These planetesimals can eventually grow into planets and moons, shaping the structure of galaxies and star systems. The presence of cosmic dust, therefore, is directly tied to the formation of the very systems that host planets like Earth. But cosmic dust doesn't only come from dying stars. It's also created in the hearts of young, forming stars. When new stars begin to form in dense molecular clouds, the energy from the young star can heat the surrounding gas and dust, causing it to glow. This process, known as emission, produces the characteristic light seen in many nebulae, the colorful, glowing clouds that adorn the night sky. The dust within these nebulae is not just part of a star-forming region, it is an integral part of the process itself. As the dust particles collide, they create new molecules and trigger chemical reactions that eventually lead to the formation of complex organic compounds. The organic molecules created in these stellar nurseries are of particular interest to scientists because of their potential role in the origins of life. These molecules can provide the basic building blocks for life as we know it, such as amino acids, proteins, and even DNA. In this way, the cosmic dust cycle has a direct link to the origins of life on Earth and potentially elsewhere in the universe. Some scientists even hypothesize that life on Earth may have been seeded by dust grains containing these complex organic compounds, brought here by comets, asteroids, or interstellar dust clouds. The potential for life elsewhere in the universe is a fascinating concept, and cosmic dust plays a central role in this search. As we study exoplanets, planets that orbit stars outside our solar system, we are also studying the dust that surrounds them. By examining the composition of the dust in the atmospheres of exoplanets, we can learn about the chemical makeup of these planets and their potential habitability. The dust around exoplanets may contain the very same organic compounds that exist in our own solar system, hinting at the possibility that life could exist on distant worlds. Beyond the creation of planets and the potential for life, cosmic dust also influences the overall structure of galaxies. The presence of dust in galaxies helps to shape their morphology, or their overall structure. In some galaxies, dust can block the light from stars, creating dark lanes and shadows that give galaxies their distinct appearance. In others, dust can scatter light, creating a softer, diffused glow that affects the overall brightness and color of the galaxy. These interactions between dust and light allow astronomers to map the distribution of dust throughout galaxies, giving us valuable insights into their structure and evolution. Dust also plays an essential role in the way light is absorbed and emitted by galaxies. As we mentioned earlier, dust absorbs light from stars and remits it in the infrared spectrum. This process, known as thermal emission, is a key factor in our understanding of the energy balance within galaxies. The dust not only absorbs and remits light, but it can also interact with the gas in the galaxy, leading to the formation of new stars and influencing the rate of star formation. The presence of dust, therefore, has a direct impact on the way galaxies evolve over time. The study of cosmic dust isn't just confined to the large-scale properties of galaxies and stars. It also has important implications for understanding our own solar system. For instance, dust particles from comets and asteroids can provide us with clues about the early solar system, and even about the conditions that existed before Earth was formed. By studying the dust particles trapped in the solar wind, scientists can learn about the composition of these ancient bodies and gain insights into the processes that led to the formation of planets. In addition, the role of cosmic dust in Earth's atmosphere is something we are only beginning to understand. When dust particles from space enter Earth's atmosphere, they can interact with the planet's climate and weather patterns. For example, cosmic dust can help to seed clouds, influencing precipitation and weather systems. Some scientists even suggest that dust particles from space may play a role in regulating the Earth's climate by reflecting sunlight and cooling the planet. This is a particularly important area of research as we continue to face the challenges of climate change. Understanding how cosmic dust interacts with our atmosphere could lead to new insights into how we might mitigate the effects of global warming. At a broader level, the cosmic dust cycle serves as a reminder of the interconnectedness of all things in the universe. From the formation of stars to the creation of planets and the potential for life, dust is an essential ingredient in the ongoing story of the cosmos. It's easy to overlook something so small, but without it, the universe as we know it would not exist. It's a fundamental building block, a key player in the ongoing process of creation and destruction that shapes the evolution of everything from galaxies to life itself. What is truly awe-inspiring is how this cycle of dust continues, influencing the universe in ways we may not yet fully understand. As we continue to study cosmic dust, we may unlock new mysteries about the nature of the universe and our place within it. Whether it's the birth of a star, the formation of a planet, or the potential for life on distant worlds, cosmic dust remains a silent, yet powerful force shaping the cosmos. The cosmic dust cycle doesn't just affect stars and planets, it also leaves a lasting impact on the very fabric of the universe. When we think about dust, we often imagine something insignificant, something that gathers on the surfaces of our furniture. But in the cosmic realm, dust is far from trivial. It's integral to the birth and death of stars, planets, and even the molecules necessary for life. It is at the heart of cosmic recycling, a process that constantly reshapes the universe, ensuring that nothing in space remains static for too long. As dust travels through space, it doesn't always follow a predictable path. It is influenced by gravitational forces, magnetic fields, and even radiation pressure from stars. These forces cause dust grains to scatter in all directions, which means that dust particles that form in one region of space can eventually end up far from their origin, influencing areas far beyond their birthplace. This is part of what makes the dust cycle so complex and dynamic. It's not just a linear process. Dust grains are constantly moving, interacting, and evolving, contributing to an ongoing cosmic exchange that spans billions of years. One of the ways this interaction happens is through the process of dust accretion. As dust grains move through space, they can collide with other particles, slowly building up larger structures. Over time, these grains can come together to form planetesimals, which are the building blocks of planets. This process, which is thought to be key to the formation of planetary systems, can take millions of years. As dust accumulates and collides, it forms larger and larger clumps, eventually resulting in the formation of rocky planets and icy bodies in the outer regions of a star system. Interestingly, this accretion process is not just confined to the formation of planets. It also plays a role in the creation of moons, asteroids, and comets. In fact, many of the comets that we observe today are thought to be remnants from this early stage of planetary formation. These icy bodies contain some of the oldest and most primitive material in the solar system, and studying them can give us clues about the conditions that existed during the birth of our own planet. As dust continues its journey through space, it can also undergo various forms of destruction. When dust grains encounter powerful radiation from a star, they can be broken apart, a process known as dust sublimation. The intense heat from a star can cause the dust particles to evaporate, releasing the elements that made up the dust into the surrounding space. This is another form of cosmic recycling, where the dust is broken down and its components are released back into the interstellar medium, where they can be reused in the creation of new stars, planets, and other cosmic structures. In addition to radiation, dust particles can also be destroyed by collisions with other objects in space. When two dust grains collide, the impact can cause them to shatter, producing even smaller fragments. These smaller particles can then become part of a new cycle of dust formation, further contributing to the complex dynamics of the cosmic dust cycle. Dust plays a crucial role in the formation of stars as well. In the dense molecular clouds that are the birthplaces of new stars, dust helps to cool the gas, enabling it to clump together under the force of gravity. This clumping of gas and dust leads to the creation of protostars, the early stages of star formation. Without the presence of dust, these clouds of gas would not be able to collapse and form new stars. Dust also serves as a catalyst for the formation of molecules in these clouds, which is an essential step in the creation of new compounds, including organic molecules that could eventually lead to life. What's remarkable is that, despite being so small, these dust particles have a profound effect on the universe. They are capable of shaping entire galaxies, influencing the formation of stars and planets, and potentially even playing a role in the development of life itself. Their role in the larger cosmic cycle is a reminder of how interconnected everything in the universe truly is. The dust from a dying star can eventually contribute to the formation of a new solar system, and the dust from that system could eventually form new stars and planets elsewhere in the universe. In this way, the cycle of cosmic dust is a continuous, ongoing process that shapes the very structure of the cosmos. As we continue to observe and study the cosmos, we gain new insights into the role that dust plays in shaping the universe. Whether it's through the formation of stars, the creation of planets, or the potential for life, cosmic dust remains a vital force in the ever-evolving story of the cosmos. In many ways, it's the unsung hero of the universe, a seemingly small but immensely powerful force that helps to shape everything we see around us. We may not fully understand all of the nuances of the cosmic dust cycle just yet, but what we do know is enough to reveal the vast interconnectedness of the universe. From the earliest moments of star formation to the birth of planets and the potential for life, cosmic dust is a constant presence, shaping the universe in ways both visible and invisible. It serves as a reminder that, even in the vast emptiness of space, the most minute particles play a crucial role in the creation and destruction of everything around us. The cosmic dust cycle is not just a scientific curiosity, it is a fundamental aspect of the universe's ongoing transformation. As we continue to explore the far reaches of space, we will undoubtedly uncover more secrets about the dust that permeates every corner of the cosmos. And who knows? Perhaps in the future, we'll even learn that the dust scattered throughout the universe carries the key to unlocking the deepest mysteries of life, the cosmos, and everything in between. As we journey further into understanding the cosmic dust cycle, it becomes clear that this seemingly minor phenomenon is far more intricate and important than we first imagined. Beyond its role in star and planet formation, cosmic dust has a profound impact on the very nature of galaxies themselves. The way dust interacts with the light from stars and other cosmic objects shapes how we observe distant parts of the universe, influencing our understanding of the cosmos as a whole. In the vast, dark regions of space, dust serves as a shield, blocking and scattering light in ways that obscure our view of the universe. These dust clouds, often found in the spiral arms of galaxies, can create nebulae, giant, colorful clouds of gas and dust. Some of these clouds are the birthplaces of new stars, while others are the remnants of older stars that have long since exploded. The dense nature of these clouds prevents light from escaping, which is why they appear dark against the backdrop of the brighter stars around them. However, not all of the dust's interactions with light are so straightforward. In fact, cosmic dust can sometimes play the role of a lens, bending and distorting light as it passes through. This phenomenon, known as gravitational lensing, can magnify and distort the images of distant galaxies, allowing astronomers to study objects that would otherwise be too faint to see. The dust, in this sense, becomes a cosmic tool, a way for scientists to peer deeper into the universe and uncover its secrets. But while dust can block or magnify light, it also has another crucial role to play, influencing the chemical composition of the universe. Dust grains are not simply inert particles floating through space. They are active participants in the chemical reactions that take place in the interstellar medium. Over time, as dust grains collide and interact with other particles, they can become coated with layers of molecules, ranging from simple compounds to more complex organic molecules. These molecules, in turn, can play a role in the formation of new stars and planets. In some cases, cosmic dust provides the essential ingredients for the formation of life. The organic molecules found on dust grains are believed to have been some of the building blocks that eventually led to life on Earth. The idea that life on our planet could have originated from cosmic dust is a fascinating concept that blurs the line between chemistry, biology, and astronomy. It suggests that the very dust that fills the universe may have played a part in the creation of life itself, a thought that lends a certain poetry to the cycle of cosmic dust. Beyond its role in star and planet formation, cosmic dust also contributes to the wider environmental conditions of galaxies. The dust grains in the interstellar medium can absorb energy from nearby stars, re-radiating it as infrared light. This process is an important factor in the energy balance of galaxies, influencing the temperature and density of gas clouds. Without dust, the universe would look very different. The way galaxies form, evolve, and interact with each other could change drastically, highlighting just how crucial this seemingly insignificant substance is. In some cases, dust can even trigger the collapse of gas clouds, leading to the formation of new stars and planetary systems. The presence of dust in molecular clouds serves to cool the gas, making it easier for the cloud to collapse under its own gravity. This process of star formation is highly complex, and dust plays a central role in enabling it. In fact, without dust, star formation as we know it might not even be possible. Dust doesn't just help to shape the stars, it also aids in the formation of the planets that orbit them. As stars reach the end of their lives, they expel vast amounts of material into space, including large quantities of dust. This material is often rich in heavy elements, which have been formed in the star's core over the course of its life. When a star dies, it releases this material into the surrounding space, enriching the interstellar medium and contributing to the cycle of cosmic dust. The dust left behind by a dying star can provide the necessary components for the creation of new stars, planets, and even life. This act of recycling, where materials from one generation of stars are used to create the next, is a key part of the cosmic dust cycle. When we look at the cycle as a whole, it becomes apparent that cosmic dust is not just a passive presence in the universe. It is a dynamic, active participant in the ongoing evolution of galaxies, stars, and planets. Dust doesn't just form in the aftermath of stars. It is continually reshaped and transformed as it travels through space. Whether it's cooling gas clouds, triggering the formation of stars, or contributing to the building blocks of life, cosmic dust is involved in nearly every significant process in the universe. The cosmic dust cycle also offers a glimpse into the future. As we continue to explore the cosmos and develop new technologies, we may gain a deeper understanding of how dust interacts with the larger forces of the universe. Perhaps one day, we will learn how to harness the power of cosmic dust, using it to fuel the creation of new stars, planets, or even artificial habitats. The potential applications of this knowledge are vast, and the possibilities are limited only by our imagination. Moreover, as we delve deeper into the study of cosmic dust, we begin to see the ways in which it can affect our understanding of distant parts of the universe. By studying the dust in the interstellar medium, astronomers can learn about the history of star formation, the chemical composition of distant galaxies, and even the conditions that led to the birth of our own solar system. Cosmic dust, then, serves as a time capsule, preserving the secrets of the universe and offering clues about its past, present, and future. The study of cosmic dust is still in its early stages, and there is much more to discover. As new telescopes and space probes are launched into the cosmos, we will undoubtedly gain new insights into the role that dust plays in shaping the universe. Perhaps one day, we will uncover even more hidden mysteries about the cycle of cosmic dust and its impact on the cosmos as a whole. The more we learn about cosmic dust, the more we realize that it is not just a byproduct of stellar processes but an essential ingredient in the ongoing creation and transformation of the universe. Its role in star formation, planet creation, and even the potential for life itself cannot be overstated. It serves as a reminder of the interconnectedness of all things in the cosmos, highlighting the ways in which even the smallest particles can have a profound effect on the larger picture. As we continue to unravel the mysteries of the cosmic dust cycle, we gain a deeper appreciation for the complexity of the universe. We are reminded that, in space, nothing is truly insignificant. Every particle, no matter how small, has a role to play in the grand scheme of things. The cycle of cosmic dust is a never-ending process of creation and destruction, shaping the universe in ways that we are only just beginning to understand. As we journey further into the mysteries of the cosmic dust cycle, we encounter even more intriguing aspects of this fascinating process. One of the most profound implications of cosmic dust lies in its contribution to the chemical enrichment of the universe. As dust grains travel through space, they encounter gas clouds, and in this environment, various chemical reactions take place. These reactions can form new molecules, including complex organic compounds. Over millions of years, these compounds can accumulate, eventually contributing to the molecular complexity found in the building blocks of life. Dust also plays a key role in the evolution of galaxies. When stars expel material, they release not only gases but also heavy elements formed in their cores. This material, which includes dust grains, is ejected into the surrounding interstellar medium, enriching it with the ingredients needed for future star and planet formation. The cycle of dust formation and recycling helps maintain a continuous supply of raw materials for the creation of new stellar bodies. Without the dust cycle, the process of galaxy formation and evolution would likely be much slower and less efficient. The life cycle of cosmic dust is far from simple. It is a dynamic and ongoing process that shapes the entire fabric of the universe. Once dust is formed in a star, it is often swept away by powerful stellar winds or supernova explosions, only to eventually settle into the interstellar medium once again. These cycles of dust creation, dispersion, and recombination are essential to the formation of stars and planets. Without dust, the process of star and planet formation would be hindered, and the rich diversity of the universe would be impossible to achieve. One of the key features of cosmic dust that sets it apart from other celestial objects is its size. Cosmic dust particles can be as small as a few nanometers, or as large as several microns. Despite their tiny size, these particles have a significant impact on the dynamics of space. Their small size allows them to be influenced by even the faintest forces, such as radiation pressure, magnetic fields, and gravity. These interactions help guide the dust particles on their journeys through space, directing them toward the regions where they can participate in the formation of stars, planets, and even entire galaxies. In addition to their small size, cosmic dust grains also possess unique physical properties that make them important players in the interstellar medium. Many of these particles are made up of complex mixtures of materials, including silicates, carbon, and ices. These materials are highly reactive and can undergo a wide variety of chemical processes when exposed to radiation and other environmental factors. For example, cosmic dust grains can absorb and scatter ultraviolet light, influencing the temperature and chemical composition of their surroundings. In this way, dust plays a direct role in shaping the conditions for star and planet formation. Dust grains are also integral to the process of planetesimal formation, the early stages of planet formation. As dust particles collide and stick together, they form larger aggregates that eventually grow into planetesimals, the building blocks of planets. This process is known as accretion, and it is a crucial step in the formation of planetary systems. Dust can also influence the distribution of material in a protoplanetary disk, where it helps determine where planets will form. For example, in a region of a protoplanetary disk that is rich in dust, planets are more likely to form, as dust helps to draw in additional material through gravitational attraction. But dust's influence does not end there. Once planets have formed, cosmic dust continues to play a role in shaping their surfaces and atmospheres. On Earth, for instance, dust from space can influence weather patterns and even affect the composition of the atmosphere. Tiny particles of dust can travel long distances through space and reach planets like ours, where they are deposited on the surface. This process is known as cosmic dust accretion, and it helps enrich planetary surfaces with new materials. The presence of cosmic dust on a planet's surface may also provide clues about the conditions in the broader solar system and the interactions between different celestial bodies. The cycle of cosmic dust extends to the very end of a star's life. When a star reaches the end of its life cycle and undergoes a supernova explosion, it releases vast amounts of material into space, including dust. The explosion of a supernova can create new elements and scatter them throughout the universe, enriching the surrounding regions with the building blocks necessary for future generations of stars, planets, and life forms. In this way, cosmic dust plays a vital role in the ongoing cycle of star birth and death, contributing to the ongoing evolution of the universe. One of the most remarkable aspects of cosmic dust is its ability to influence the formation of planets, and even the conditions that might allow life to arise. While the dust itself is not alive, the materials it contains can be used to form the molecules necessary for life. This process is thought to have played a key role in the origins of life on Earth. Some scientists propose that the complex organic molecules found in cosmic dust may have been carried to Earth by comets or meteorites, serving as the starting point for the development of life. In this sense, cosmic dust is not just a passive material drifting through space. It is an active participant in the very process that has allowed life to flourish on our planet. In addition to its role in the formation of life, cosmic dust has practical applications in other areas of science and technology. For example, researchers are studying cosmic dust to better understand the processes that occur in the interstellar medium and the conditions that lead to the formation of stars and planets. By studying the dust that surrounds stars and galaxies, scientists can learn more about the chemical composition of the universe, as well as the physical conditions in different regions of space. In the future, it is possible that we could use cosmic dust as a resource, either to create new materials or as a way to study distant parts of the universe. The study of cosmic dust is also important for understanding the broader dynamics of galaxies. Dust grains play a central role in the formation and evolution of galaxies, as they are involved in both star formation and the cooling of gas clouds. Without dust, galaxies would likely evolve in a very different manner, as the formation of stars and planetary systems would be impeded. Dust also has an effect on the light emitted by stars, which is crucial for understanding the age and composition of distant galaxies. By studying the dust in different regions of space, scientists can learn more about how galaxies evolve and interact with each other. As we continue to learn more about cosmic dust, we gain new insights into the processes that shape the universe. From the birth of stars and planets to the formation of galaxies and the origins of life, cosmic dust plays an essential role in every step of the cosmic journey. The study of this tiny, seemingly insignificant material is helping us unravel the mysteries of the universe, and it is likely that we will continue to make exciting discoveries in the years to come. The cosmic dust cycle is far from complete, and as our understanding deepens, we may find that dust is even more important than we ever imagined. As we delve deeper into the cosmic dust cycle, we begin to uncover more layers of complexity and intrigue. One aspect of cosmic dust that is especially fascinating is its ability to influence the very structure and organization of the universe. Cosmic dust particles are not just drifting aimlessly through space. They are active participants in the shaping of the cosmos. Their movement and interactions can lead to the formation of large-scale structures such as molecular clouds, star clusters, and even galaxies themselves. Molecular clouds, also known as stellar nurseries, are vast regions of space where new stars and planetary systems are born. These clouds are dense concentrations of gas and dust, and they are essential for star formation. In these clouds, cosmic dust grains serve as the seeds around which matter can coalesce. Over time, the dust and gas come together, under the influence of gravity, to form protostars and eventually fully fledged stars. The process of star formation in molecular clouds is a key part of the cosmic dust cycle, and without dust, these clouds would not be able to condense and form new stellar objects. But the story of cosmic dust doesn't end with star formation. As stars evolve, they expel material into space, enriching the surrounding environment with new dust and gas. These stellar winds and supernova explosions release vast amounts of material, including heavy elements that are critical for the formation of planets. This material, which includes dust grains, is dispersed into the interstellar medium, where it can once again be incorporated into new molecular clouds. Thus, the cycle of dust is perpetuated, with each generation of stars and planets contributing to the ongoing process of cosmic enrichment. One of the key features of cosmic dust that makes it so essential for the formation of planets is its ability to facilitate the process of accretion. Accretion is the process by which dust particles collide and stick together to form larger objects. Over time, these objects can grow larger and larger, eventually becoming planetesimals, the building blocks of planets. This process is critical for the formation of planets and protoplanetary disks, the regions of space surrounding young stars where planets are born. Without dust, the accretion process would be far less efficient, and the formation of planets would be much more difficult. Cosmic dust is also crucial for the development of planetary atmospheres. When dust particles settle on the surfaces of planets, they can contribute to the formation of an atmosphere by introducing new gases and compounds. This process is thought to have played a significant role in the early history of Earth, where cosmic dust may have brought essential elements such as carbon and nitrogen to the planet. These elements are key building blocks for life, and their presence on Earth may have been facilitated in part by the dust that arrived from space. Beyond the formation of planets, cosmic dust also has a profound impact on the physical characteristics of celestial bodies. For example, dust particles can influence the surface temperature of planets by scattering and absorbing light. On Earth, dust from space can affect weather patterns and even play a role in the formation of clouds. In the future, as our understanding of cosmic dust deepens, it is possible that we could use it to study distant planets and moons, gaining insights into their composition and climate. The role of cosmic dust in the universe extends far beyond the local scale of individual stars and planets. Dust grains are found throughout galaxies, and they can have a significant impact on the overall evolution of these massive systems. In particular, dust plays a key role in the cooling of gas clouds within galaxies, which is essential for star formation. Without dust, the gas clouds in galaxies would not be able to cool efficiently, and the process of star formation would be significantly hindered. Dust also influences the way light is emitted by stars and galaxies. Dust grains can absorb and scatter light, changing the way we perceive distant objects in space. For example, when light from a star passes through a dust cloud, the dust can block or distort the light, making it more difficult to observe the star. This effect is known as interstellar extinction, and it is one of the reasons why some stars appear dimmer than they actually are. By studying the way light interacts with dust, astronomers can learn more about the composition and distribution of dust in different regions of space. Cosmic dust also plays a role in the broader processes of galactic evolution. As galaxies collide and merge, the dust within them is redistributed, influencing the way stars and planets form in the new, merged system. The redistribution of dust can also trigger the formation of new stars, as the gas and dust in the merging galaxies collapse under gravity. In this way, cosmic dust is not just a passive material, it is an active participant in the dynamic processes that shape the evolution of galaxies and the larger cosmic structure. One of the most intriguing aspects of cosmic dust is its ability to travel vast distances across space. Dust grains are so small that they can be affected by the faintest forces, such as radiation pressure and magnetic fields. These forces can cause dust particles to move across enormous distances, carrying them from one region of space to another. This ability to travel long distances allows dust to be spread throughout the universe, enriching different regions with the materials needed for star and planet formation. The journey of dust particles through space is not without its challenges, however. Dust grains are often subjected to intense radiation, which can cause them to break apart or undergo chemical transformations. In addition, dust particles are subject to the gravitational pull of stars and planets, which can cause them to become trapped in orbits around celestial bodies. Despite these challenges, dust continues to travel across space, playing an essential role in the creation and evolution of stars, planets, and galaxies. The study of cosmic dust is a rapidly evolving field, and with new technologies and instruments, we are learning more about dust than ever before. For example, astronomers are now able to study the composition of cosmic dust in greater detail using spectroscopic techniques. These techniques allow scientists to analyze the light emitted or absorbed by dust particles, providing valuable information about their chemical composition and structure. In the future, it is likely that we will continue to uncover new and surprising facts about cosmic dust, deepening our understanding of the universe and the processes that govern its evolution. In addition to its scientific significance, cosmic dust has practical applications in various fields of technology. For example, dust is a key component in the creation of materials used in space exploration. Dust particles can be used to develop new materials with unique properties, such as lightweight and durable materials for spacecraft. Additionally, the study of cosmic dust may help us improve our understanding of the conditions necessary for the formation of life, potentially leading to breakthroughs in the search for life elsewhere in the universe. The role of cosmic dust in the universe cannot be overstated. From its participation in the formation of stars and planets to its impact on the evolution of galaxies, cosmic dust is an essential ingredient in the cosmic recipe. As we continue to explore the mysteries of the cosmos, we are likely to discover even more about this tiny but powerful material and its role in shaping the universe. The cosmic dust cycle is far from complete, and as our understanding deepens, we may find that dust is even more important than we ever imagined. As we continue to unravel the mysteries of cosmic dust, one fascinating aspect to explore is its role in the formation and evolution of life. While dust particles may seem insignificant when compared to the massive forces at play in the cosmos, they have played a crucial part in the history of our planet and could even hold the key to understanding life's origins. The presence of cosmic dust on Earth, and its impact on our planet's atmosphere and climate, has led scientists to consider the possibility that some of the building blocks of life might have come from space itself. Cosmic dust is rich in organic molecules, including amino acids, which are the building blocks of proteins. These molecules, along with other complex organic compounds, are thought to have been delivered to early Earth through meteorites, comets, and cosmic dust particles. This process, known as panspermia, suggests that life on Earth may have had an extraterrestrial origin, with cosmic dust playing a key role in bringing the necessary ingredients for life from space. While the theory of panspermia is still a subject of debate, the discovery of complex organic molecules in cosmic dust strengthens the idea that the building blocks of life may indeed come from beyond our planet. The study of cosmic dust has also provided valuable insights into the conditions necessary for life to exist elsewhere in the universe. By analyzing the composition of dust particles found in different regions of space, scientists can learn more about the environments in which stars, planets, and life might form. For example, dust grains in molecular clouds are often found to contain complex carbon compounds, which are essential for the formation of life as we know it. These findings suggest that the conditions required for life may be more common in the universe than previously thought, raising the possibility that other planets or moons could harbor life. One of the most intriguing areas of research is the study of cosmic dust in relation to the potential habitability of exoplanets. Exoplanets, or planets that orbit stars outside of our solar system, are of particular interest to astronomers because they offer a glimpse into the diversity of planetary systems that exist in the universe. By studying the dust surrounding these exoplanets, scientists can gather information about the planet's atmosphere, composition, and potential for life. Dust particles can provide clues about the presence of water, organic molecules, and other key ingredients for life, making them an invaluable tool in the search for habitable worlds. The discovery of cosmic dust on distant exoplanets could also have profound implications for our understanding of how planetary systems form. When a star forms, it is surrounded by a protoplanetary disk made up of gas and dust. Over time, this dust and gas come together to form planets, moons, and other celestial bodies. By studying the dust in these disks, astronomers can learn more about the conditions that lead to planet formation and the types of planets that are likely to exist around different types of stars. This research is crucial for understanding the diversity of exoplanets and their potential for habitability. The cosmic dust cycle also offers insights into the broader processes of galactic evolution. As galaxies form and evolve, the dust within them plays a significant role in shaping the structure and dynamics of these systems. For example, dust can influence the rate of star formation within galaxies by cooling the gas clouds that are necessary for the birth of new stars. Without dust, these gas clouds would remain too hot to condense, making star formation much more difficult. In this way, cosmic dust is a critical factor in the ongoing process of galactic evolution, and its presence or absence can have a profound impact on the development of galaxies over time. The distribution of cosmic dust across the universe is also an important factor in understanding the large-scale structure of the cosmos. Dust particles are not evenly distributed throughout space. Instead, they tend to concentrate in certain regions, such as molecular clouds, star-forming regions, and the interstellar medium of galaxies. These concentrations of dust play a crucial role in the formation of stars and planetary systems. By studying the distribution of dust, astronomers can map out the structure of galaxies and gain insights into the processes that govern their evolution. In recent years, advances in telescope technology have allowed astronomers to study cosmic dust in greater detail than ever before. The launch of space-based observatories, such as the Hubble Space Telescope and the James Webb Space Telescope, has provided unprecedented views of distant galaxies, star-forming regions, and protoplanetary disks. These observations have led to the discovery of previously unknown aspects of cosmic dust, including its role in the cooling of gas clouds, its impact on the formation of stars and planets, and its ability to travel vast distances across the cosmos. One of the most exciting aspects of this research is the potential for future discoveries about the origin and evolution of cosmic dust. As we continue to explore the universe, new technologies and techniques will allow us to study dust in even greater detail, uncovering its many secrets and shedding light on its crucial role in the cosmic cycle. In the coming decades, astronomers hope to learn more about the chemical composition of dust particles, the processes by which they form, and how they interact with other materials in space. These discoveries will not only deepen our understanding of the universe but also help us answer some of the most profound questions about the nature of life and the origins of the cosmos. In addition to its scientific significance, cosmic dust has practical applications in various fields, including space exploration and materials science. For example, the study of cosmic dust can help scientists develop new materials for spacecraft, satellites, and other space-based technologies. Dust particles can be used to create lightweight and durable materials with unique properties, such as radiation resistance and thermal insulation. These materials are essential for protecting spacecraft from the harsh conditions of space, where extreme temperatures and radiation can damage sensitive equipment. Cosmic dust also has the potential to contribute to the development of new technologies here on Earth. Researchers are exploring ways to use dust particles in the creation of advanced materials for use in industries such as electronics. As we learn more about the properties of cosmic dust, it is likely that new applications will emerge, further expanding the possibilities for this remarkable material. The cosmic dust cycle is a testament to the interconnectedness of the universe. From its formation in the cores of stars to its journey through space and eventual contribution to the birth of new stars and planets, cosmic dust plays an essential role in the ongoing evolution of the cosmos. Its impact on star formation, planet building, and even the development of life highlights the importance of this seemingly insignificant material. As we continue to study cosmic dust and its role in the universe, we are likely to uncover even more astonishing discoveries that will deepen our understanding of the cosmos and our place within it. Cosmic dust is far from being just a byproduct of space. It is a crucial component of the universe's evolutionary process. Whether it's facilitating the formation of stars and planets, influencing the development of atmospheres, or potentially even playing a role in the origins of life itself, cosmic dust is central to the way the universe functions. As we continue to explore the mysteries of the cosmos, the study of cosmic dust will undoubtedly remain at the forefront of astronomical research, offering new insights into the complex and fascinating processes that shape the universe. The journey of dust, from star to star, from galaxy to galaxy, is a never-ending cycle, one that will continue to unfold as we strive to understand the true nature of the universe. As we continue to explore the cycle of cosmic dust, it's important to consider the cosmic significance of these minute particles in the larger picture of cosmic evolution. Dust, although seemingly insignificant in comparison to the massive stars and galaxies that populate our universe, is crucial in shaping the structure and behavior of the cosmos at multiple scales. The ability of cosmic dust to influence the formation of galaxies, stars, and planetary systems cannot be overstated. It stands at the very foundation of the processes that drive the growth and evolution of the universe. One of the key aspects of cosmic dust that has intrigued scientists for decades is its role in the formation of interstellar clouds. These clouds, which are often the birthplaces of new stars, are composed of both gas and dust, and they serve as the incubators for the next generation of celestial bodies. In these clouds, dust particles play a pivotal role in cooling the surrounding gas, allowing it to condense into dense clumps where stars can form. Without this dust, the gas would remain too hot, preventing the collapse needed for the birth of stars. This mechanism makes dust an indispensable player in star formation, influencing the size and mass of new stars that eventually emerge. Dust's cooling effect in molecular clouds is not just a matter of temperature regulation. It also plays a significant role in determining the chemical composition of the stars and planets that form from these clouds. The dust grains, composed of elements like carbon, silicon, and iron, can interact with the surrounding gas, fostering chemical reactions that lead to the formation of more complex molecules. These molecules, in turn, contribute to the diversity of elements and compounds found in stars and planets. The dust grains themselves are like a chemical laboratory, constantly reacting with gases in the surrounding space, ultimately influencing the properties of the stars and planets that will emerge. The relationship between dust and star formation also leads to an intriguing connection with the life cycle of stars. As stars evolve, they expel material back into space through various processes such as stellar winds, supernova explosions, and planetary nebulae. This material includes a significant amount of dust, which is enriched with the elements forged in the star's core. This dust, along with gas, is then dispersed into the surrounding interstellar medium, enriching it with heavy elements that can later be incorporated into the formation of new stars, planets, and even life itself. This recycling process is an essential component of the cosmic dust cycle, allowing for the ongoing creation and destruction of matter throughout the universe. In many ways, the life cycle of dust mirrors the life cycle of stars. Just as stars are born, evolve, and eventually die, so too are dust particles created, transformed, and ultimately dispersed into the cosmic ether. The cycle of dust particles is ongoing, with each generation of dust playing a role in the birth of the next. This cycle is a key component of the broader cosmic ecosystem, ensuring that the building blocks of stars, planets, and life are continually replenished. Beyond their role in the formation of stars and planets, cosmic dust particles are also instrumental in shaping the properties of galaxies. Galaxies are vast collections of stars, gas, and dust, and the distribution of dust within a galaxy can influence its overall structure and behavior. For example, dust can block or absorb light from stars, affecting the way we observe galaxies from a distance. In some cases, the presence of dust can obscure the central regions of galaxies, making it difficult to study the full extent of their structure. In other cases, dust can serve as a catalyst for star formation, fostering the birth of new stars in the heart of the galaxy. One of the most interesting aspects of the cosmic dust cycle is the role it plays in the intergalactic medium. While most of the universe's dust is found within galaxies, a significant amount also exists in the vast spaces between galaxies, in what is known as the intergalactic medium. This dust is often dispersed through interactions between galaxies, such as galaxy collisions or the merging of galactic clusters. When galaxies collide, the dust from each galaxy is mixed together, enriching the intergalactic medium with new elements and compounds. This process not only influences the structure of the galaxies involved but also affects the behavior of the intergalactic medium itself, which in turn can impact the formation of new galaxies and stars in the future. In the broader cosmic context, cosmic dust plays an essential role in regulating the dynamics of the universe. By influencing the rate of star formation, the chemical composition of celestial bodies, and the evolution of galaxies, dust is a driving force in the ongoing transformation of the cosmos. It helps to create the conditions necessary for the emergence of new stars and planets, as well as the possibility of life. Dust's presence in the universe is a constant reminder that even the smallest particles can have a profound impact on the larger-scale processes that shape the universe. Interestingly, the study of cosmic dust also has practical applications here on Earth. By understanding how dust interacts with light and heat, scientists have been able to develop new technologies that can be applied in fields such as astronomy, climate science, and even materials engineering. For example, the study of cosmic dust has led to the development of more efficient ways to detect exoplanets, using the way dust grains scatter light to determine the properties of distant worlds. In climate science, dust plays a significant role in regulating the Earth's temperature by influencing the amount of sunlight that reaches the surface. Dust storms, such as those that occur in deserts, can have a dramatic effect on weather patterns, and understanding the role of cosmic dust in Earth's climate system helps scientists better predict and understand these phenomena. In the realm of materials science, the properties of cosmic dust have inspired researchers to develop new materials with unique characteristics. The incredibly fine, lightweight, and heat-resistant nature of dust particles makes them ideal for creating advanced materials that can withstand extreme conditions. For example, cosmic dust-inspired materials are being explored for use in spacecraft, as they could provide a lightweight, durable solution for building protective coatings and insulation. Additionally, the study of cosmic dust could lead to breakthroughs in the development of new types of nanomaterials. In a sense, cosmic dust connects us to the universe in a very tangible way. It is a constant presence, traveling through space and time, shaping the formation of stars, planets, and galaxies. While we may not always be able to see it, the effects of cosmic dust are everywhere, influencing the evolution of the cosmos and the very conditions that make life possible. As we continue to study cosmic dust and its many mysteries, we are bound to uncover even more about the nature of the universe and our place within it. As we continue to delve deeper into the cosmic dust cycle, it's clear that its significance reaches far beyond just star and planet formation. Dust plays a pivotal role in shaping the very fabric of the universe, affecting everything from the colors of distant galaxies to the potential for life on planets like Earth. One of the most intriguing aspects of cosmic dust is how it interacts with light. When we look at distant galaxies, we are often seeing the combined effects of stars, gas, and dust. The dust in these galaxies can absorb and scatter light, altering the way we perceive these distant objects. This phenomenon is known as extinction. It can make distant stars and galaxies appear dimmer than they actually are, a fact that astronomers must account for when measuring the distance to these objects or studying their internal properties. In some cases, dust can even block our view of certain regions of space entirely, leaving vast cosmic regions obscured from view. Yet, despite this obscuring effect, dust is also responsible for some of the most striking visual features of the universe. For instance, the dark lanes we often see across the bright, glowing regions of galaxies or nebulae are caused by dense concentrations of dust blocking the light from stars behind them. These dark patches, while seemingly void of light, are often sites of intense activity, as new stars are being born within these regions. These dark regions are often where the temperature is low enough and the gas dense enough for new stars to form. So, while cosmic dust can obscure our view of the universe, it also plays a vital role in the processes that shape it. Moreover, cosmic dust grains are not uniform in composition or structure. Some are made up of silicates, while others contain carbon-rich compounds. Some grains are small, only a few nanometers in diameter, while others are much larger. The diversity in dust composition allows it to interact with light and matter in a variety of ways. For instance, silicate grains tend to scatter blue light more efficiently than red light, giving rise to the characteristic bluish haze we see in some star-forming regions. Carbon-rich dust, on the other hand, can absorb light more efficiently, sometimes giving nebulae their reddish glow. This variation in dust properties makes the study of cosmic dust a complex but rewarding endeavor. Another fascinating aspect of cosmic dust is its role in the formation of planetary systems. As dust grains collide and stick together over time, they form larger and larger objects, eventually leading to the formation of planets. The process begins with the condensation of dust into small grains that can aggregate in the low-pressure environments found in molecular clouds. These grains then collide and stick together through electrostatic forces, eventually forming larger clumps that can become the building blocks of planets. The ability of dust to accumulate and condense into solid bodies is crucial for the formation of planets and other celestial objects. Without this process, planets as we know them would not be able to form. In fact, our own solar system provides a perfect example of the role of cosmic dust in planet formation. The dust and gas that were present in the early solar system are thought to have come together to form the Sun, the planets, and all the other objects that make up the solar system. As dust grains collided and stuck together, they gradually formed larger bodies known as planetesimals. These planetesimals then collided with one another, eventually forming the planets. This process is known as accretion, and it is thought to have taken place in the early stages of the solar system's formation. Without cosmic dust, the material that would form the Earth and other planets would not have been able to condense, and the solar system would have remained a chaotic mix of gas and dust. However, the role of dust in planet formation doesn't end once a planet has formed. Dust is also an essential ingredient in the formation of planetary atmospheres. During the early stages of a planet's development, dust particles can be incorporated into its atmosphere, contributing to the formation of clouds, weather patterns, and even the chemistry of the planet's surface. On Earth, for example, the dust that travels through space and enters our atmosphere plays a significant role in the planet's weather systems. Dust particles can act as nuclei for the formation of clouds, influencing precipitation patterns and even the overall climate. Furthermore, the study of cosmic dust also provides important clues about the conditions present on distant planets and moons. By studying the dust around other stars, astronomers can infer the types of planets and moons that may be orbiting them. For example, the presence of certain types of dust in the interstellar medium can suggest the presence of rocky planets, while other dust compositions may indicate gas giants or icy moons. This information can help scientists identify planets that may have conditions suitable for life, or at the very least, help them narrow down the search for potentially habitable worlds. One particularly interesting aspect of cosmic dust is its role in the so-called galactic habitable zone. Just as the Earth resides in a habitable zone around the Sun, there are regions of galaxies where the conditions are more favorable for the formation of life. These regions, often located in the spiral arms of galaxies, are rich in gas and dust, providing the raw materials for star and planet formation. The presence of cosmic dust in these regions is a key factor in the likelihood of life emerging. Dust provides the necessary building blocks for life as we know it, and its presence in the galactic habitable zone makes these regions prime candidates for the development of life. Despite its importance, cosmic dust is not always benign. In some cases, dust can cause problems for both astronomers and space travelers. For example, cosmic dust can be a major hindrance to the study of distant galaxies, as it can obscure our view of certain regions of space. For a spacecraft venturing into the vastness of space, dust poses a significant hazard, as even small dust particles can cause significant damage to spacecraft. This is especially true in regions with high concentrations of dust, such as near the edges of galaxies or in the dense clouds of gas and dust that surround young stars. Dust particles can collide with spacecraft at incredibly high speeds, potentially damaging critical equipment, or even causing the spacecraft to fail. But beyond the challenges, there's also a sense of awe that comes from understanding the role that cosmic dust plays in the grand scheme of the universe. It's humbling to think that something so small and seemingly insignificant can have such a profound impact on the creation of stars, planets, and even life itself. Every grain of dust carries with it the potential for new beginnings, new stars, new planets, and maybe even new forms of life. It's a reminder that, in the vast expanse of space, even the smallest particles have a role to play in shaping the cosmos. The cosmic dust cycle is a reminder of the interconnectedness of all things in the universe. It shows us that everything, from the stars we see twinkling in the night sky to the planets we might one day explore, is part of an ongoing cycle of creation, destruction, and rebirth. Dust, in all its forms, is at the heart of this cycle. It's the foundation of stars, the building blocks of planets, and a key component in the ongoing evolution of the universe. In many ways, cosmic dust is the glue that holds the universe together, ensuring that the process of cosmic evolution continues unabated, one grain of dust at a time. And perhaps, as we look deeper into the mysteries of cosmic dust, we'll come to understand even more about the origins of the universe itself. After all, just as dust can be found at the heart of stars and galaxies, it might also hold the answers to some of the deepest questions about the nature of existence. How did it all begin? What role does dust play in the unfolding story of the cosmos? These are questions that we may one day answer, thanks to the humble particles of cosmic dust. As we continue our exploration of the cosmic dust cycle, it's essential to understand that dust isn't just something that resides in deep space, quietly drifting between the stars. It is an active participant in the cosmic dance that has been shaping the universe since the very beginning. When we talk about dust, we're not just referring to the microscopic grains that we might find on Earth. In the vastness of space, cosmic dust can come in many forms, including silicates, carbon compounds, and even metals. This makes it far more interesting than the simple dust we find on our furniture or in the corners of our rooms. Now, let's think about the broader implications of cosmic dust. It's not just about planet and star formation, though that's a major aspect. Dust has profound effects on the entire structure and evolution of galaxies. When galaxies form, they don't do so out of thin air. They're built from the materials scattered throughout space: gas, dust, and radiation. These elements combine to form massive clouds of matter that collapse under their own gravity, eventually forming the structures that we see in the universe today. Without the presence of dust in these clouds, the process of galaxy formation would look drastically different. Dust helps cool the gas within these clouds, allowing it to condense and form stars and planets. Without this cooling effect, the gas would remain too hot and diffuse to form solid structures. Moreover, dust can also play a role in the creation of supernovae. These colossal explosions are one of the universe's most dramatic events, and they are known to release vast amounts of energy and elements into space. Some of these elements will eventually become part of new stars, planets, and even life. Dust plays a vital part in the aftermath of these explosions, helping to redistribute the elements that form the building blocks of future cosmic bodies. In essence, dust is both a participant and a product of the universe's life cycle. Another important aspect to consider is the relationship between cosmic dust and star formation. When a region of a galaxy is rich in gas and dust, it creates an environment where new stars can be born. This process begins in molecular clouds, where dust helps to shield the gas from heat and radiation, allowing it to cool and condense into clumps that eventually form stars. As these new stars are born, they are surrounded by dust and gas that continues to interact with the young stars, sometimes forming disks of material that can later become planets. This dynamic relationship between stars and dust helps to explain why some regions of galaxies are more active in terms of star formation than others. Interestingly, cosmic dust also plays a part in the way that galaxies interact with one another. When galaxies collide, the dust within them can be pushed around, compressed, or even destroyed by the immense forces at play. This can lead to the formation of new stars, as the gas and dust are squeezed together, triggering the process of star formation. At the same time, dust can be expelled from galaxies during such collisions, further spreading the building blocks of the universe throughout space. These interactions are a testament to the dynamic nature of the universe, where nothing is static and everything is constantly in flux. But perhaps one of the most fascinating aspects of cosmic dust is its role in the potential for life beyond Earth. Dust doesn't just help form stars and planets, it may also contribute to the conditions necessary for life. For instance, the presence of certain carbon-based molecules in cosmic dust suggests that the building blocks of life may be scattered throughout the universe. This has profound implications for the search for extraterrestrial life. If dust is carrying the ingredients for life across the cosmos, it means that life may not be as rare as we once thought. Perhaps, rather than being confined to Earth, life could be spread across distant planets, just waiting for the right conditions to take hold. This idea has led to the fascinating field of astrobiology, which explores the potential for life beyond Earth. Scientists have studied meteorites and cosmic dust samples that have fallen to Earth in search of organic compounds that could be precursors to life. Some of these samples have revealed amino acids and other complex molecules, suggesting that the fundamental building blocks of life may be more widespread than we realize. If these molecules are found on other planets or moons, it could dramatically increase the chances of discovering life elsewhere in the universe. Yet, despite its potential for life, cosmic dust can also be a force of destruction. The very same dust that helps create stars and planets can also pose a threat to spacecraft and space missions. Dust particles, while tiny, are often traveling at incredible speeds, and even the smallest collision with a spacecraft can cause significant damage. Spacecraft such as satellites, rovers, and telescopes must be designed to withstand the impact of cosmic dust, which can be a challenge given the vastness and unpredictability of space. The study of cosmic dust and its potential dangers is an important part of space exploration, as understanding how dust behaves and how to protect equipment from its effects will be crucial for future missions. As we turn our attention to the distant future, we begin to realize that cosmic dust could play a significant role in the evolution of the universe itself. As stars age and die, they expel vast amounts of material, including dust. Over time, this dust will accumulate, forming new clouds of gas and dust that will eventually give birth to new stars and planets. This process will continue in an endless cycle, with dust acting as both the foundation and the product of cosmic creation. In this way, dust is not just a byproduct of star and planet formation, it is an integral part of the ongoing evolution of the universe. Ultimately, cosmic dust is more than just tiny particles floating through space. It is a fundamental building block of the universe, shaping everything from the formation of stars to the potential for life on distant worlds. It may be invisible to the naked eye, but its influence on the cosmos is undeniable. From the very first moments of the universe's existence to the birth of new stars and planets, dust has played a crucial role in the ongoing story of the cosmos. And as we continue to study and understand this elusive substance, we may come to realize just how deeply connected we are to the vast expanse of the universe itself. The cosmic dust cycle is a testament to the complexity of the universe. It reminds us that even the smallest particles can have a profound impact on the larger scale of things, shaping the stars, planets, and even the potential for life itself. As we continue to explore the mysteries of the cosmos, cosmic dust will undoubtedly remain a key part of the story, one that offers endless possibilities for discovery and understanding. And who knows? Perhaps one day, we will find that the dust scattered throughout the universe is not just a sign of the past, but a clue to the future of our existence in this vast and mysterious cosmos. As we move forward in exploring the cosmic dust cycle, it's critical to remember that dust isn't just a byproduct of stellar processes. It's one of the fundamental elements that give shape to galaxies, stars, planets, and possibly even life. This seemingly inconspicuous substance carries immense power, playing an instrumental role in the creation and destruction of celestial objects. As we venture deeper into the topic, it becomes increasingly clear that dust cycles through space in a pattern that mirrors the continuous birth and death of stars and galaxies. It's as if the universe itself is being continually recycled, with dust as its primary currency of transformation. Dust particles begin their journey in the cores of stars, the places where nuclear fusion occurs, and elements are created under extreme pressure and heat. Stars generate an extraordinary amount of energy through the fusion of lighter elements, and during this process, they create heavier elements like carbon, oxygen, and iron. These heavier elements are what form the solid matter we associate with dust. When stars reach the end of their life cycle, they expel these elements into space through powerful stellar winds or during a supernova explosion. This release of matter serves as the first step in the dust cycle, as the expelled material is dispersed across vast regions of space, enriching the interstellar medium with the building blocks necessary for the creation of new stars, planets, and even potential life forms. This material, now spread out across space, is not static. Over time, the elements begin to clump together under the force of gravity, forming small grains of dust. These dust grains can range in size, from minuscule particles smaller than the width of a human hair to larger clumps that are still small in comparison to planets and stars. As dust grains accumulate, they can become part of a much larger structure, such as a nebula, a giant cloud of gas and dust where new stars are born. Within these nebulae, dust helps facilitate the cooling of the gas, allowing it to collapse under its own gravity and form new stars. One of the most fascinating aspects of cosmic dust is its ability to both hinder and aid star formation. While dust cools the gas in nebulae, encouraging it to collapse and form new stars, it can also obscure the view of these star-forming regions. In fact, dust is one of the reasons why astronomers often use infrared telescopes to observe regions of space where stars are being born. The dust absorbs and scatters visible light, blocking our direct view of these regions. However, it also remits energy in the form of infrared radiation, which we can detect with specialized instruments. This means that while cosmic dust might be a barrier to visible light, it simultaneously provides us with a unique window into the processes that are otherwise hidden from view. As stars continue to evolve, the role of dust doesn't end there. In fact, the presence of dust is integral to the process of planetary formation. As new stars are born, they are often surrounded by a disk of dust and gas. This disk, known as a protoplanetary disk, is where planets are formed. Dust grains within the disk collide and stick together, gradually building up larger bodies that will eventually become planets. These small grains of dust are the building blocks of the worlds that orbit stars, and they provide a direct connection between the cosmic dust cycle and the formation of planetary systems. Interestingly, the dust doesn't always settle into just one place in space. It can be ejected from its point of origin, sometimes being pushed to the far reaches of a galaxy, where it can remain for eons, wandering through the cosmos. During this journey, dust interacts with various phenomena, such as radiation from stars or shock waves from supernovae. These interactions can alter the composition and behavior of the dust, sometimes causing it to break apart or combine with other materials. This dynamic, ever-changing process ensures that dust is constantly being reshaped and redistributed throughout the universe. Cosmic dust also contributes to the formation of the most extreme cosmic objects, black holes. When large clouds of gas and dust collapse under their own gravity, they can form the conditions necessary for the creation of a black hole. These massive, invisible objects exert such strong gravitational forces that not even light can escape their pull. Interestingly, it's often the dust within these collapsing clouds that serves as the catalyst for the formation of black holes, highlighting the essential role that dust plays in the creation of some of the most mysterious and powerful objects in the universe. Yet, as much as cosmic dust is involved in creating new stars, planets, and galaxies, it is equally a part of the process of their destruction. As stars reach the end of their life cycles, they can expel dust into space during events like supernovae, or even in quieter deaths, like planetary nebulae. These violent deaths of stars are crucial for enriching the interstellar medium with the heavier elements that will eventually form new stars and planets. However, as stars explode or shed their outer layers, they create waves of dust that will eventually disperse into the surrounding space, adding another layer of complexity to the cosmic dust cycle. The impact of this dust on the broader scale of the universe is significant. Dust can alter the properties of galaxies, influence the formation of stars, and even play a role in the chemistry of the interstellar medium. Without dust, the process of star formation would be far less efficient, and the formation of planets would be a much rarer occurrence. The presence of dust, in all its complexity, is what makes the universe an ever-evolving and dynamic place. It connects the death of one star to the birth of another, creating a cycle that has been ongoing for billions of years. As we look beyond our solar system and beyond even the Milky Way galaxy, it's clear that cosmic dust is not unique to our corner of the universe. It is present in galaxies far, far away, contributing to the same processes of star and planet formation that we observe in our own galaxy. In fact, studies of distant galaxies have revealed the presence of dust grains in regions where new stars are being born, further cementing the idea that dust is an essential component of the universe's life cycle. Ultimately, the cosmic dust cycle reveals the interconnectedness of the universe. Dust, while seemingly small and insignificant, plays an essential role in shaping the cosmos. It is part of an ongoing process of creation and destruction, where the birth of new stars and planets is intimately linked with the death of old ones. It is this cycle of life and death, creation and destruction, that keeps the universe in constant motion, constantly evolving. So, as we gaze up at the night sky and wonder about the mysteries of space, it's important to remember that the dust we see, whether through the lens of a telescope or in the form of interstellar clouds, has an incredible story to tell. It's a story of cosmic recycling, of the building blocks of life and planets scattered across the vast expanse of space, and of the never-ending dance between creation and destruction. And as we continue to explore and understand the universe, cosmic dust will undoubtedly remain at the heart of the cosmic cycle, quietly shaping the stars, planets, and galaxies that make up the cosmos. As we continue to explore the cosmic dust cycle, it's important to recognize the profound impact that dust has not only on the formation of stars and planets, but also on the chemical evolution of the universe. Dust is the repository of all the elements that are created inside stars, and as it circulates through space, it serves as a kind of cosmic recycling system, enabling the same atoms to be reused over and over again in different forms. Cosmic dust grains are made up of a variety of elements, primarily carbon, silicon, oxygen, and iron, and these elements are key to the formation of molecules like water, carbon dioxide, and even the complex organic compounds that could potentially support life. As stars go through their life cycles, they forge heavier elements in their cores. When these stars die, whether through supernova explosions or through quieter deaths like planetary nebulae, they release these elements into the surrounding space in the form of dust. Over time, the dust accumulates and becomes part of new molecular clouds, where it can again participate in the creation of stars and planets, forming the basis for the next generation of celestial objects. This ongoing cycle of creation and destruction, death and rebirth, is what drives the chemical evolution of galaxies. The elements created in stars are scattered into the interstellar medium, where they can be captured by new generations of stars, planets, and even potential life. This continuous recycling of matter is what ensures that the universe remains a dynamic and evolving place. In fact, the very atoms that make up your body, carbon, oxygen, nitrogen, and many others, were once part of cosmic dust, having traveled through space from previous generations of stars. The idea that we, as humans, are made of stardust is not just poetic, it's a scientific reality. These atoms were forged in the hearts of long-dead stars and have been part of the cosmic dust cycle, traveling through space, being captured by new stars, and eventually becoming part of planets and life forms, including us. One of the fascinating aspects of cosmic dust is its role in the chemical processes that take place in space. In the cold, dark regions of space, dust grains act as catalysts for the formation of complex molecules. For example, dust grains can serve as a surface where simple molecules like hydrogen and oxygen can react and form water, an essential molecule for life as we know it. This process, known as dust catalysis, happens in molecular clouds, where the temperature is just a few degrees above absolute zero. The dust grains provide a surface where atoms and molecules can interact and form new compounds, which are then incorporated into the gas and dust mixture that makes up these clouds. In this way, dust helps build the complex molecular inventory needed for star and planet formation, as well as for the potential emergence of life. Cosmic dust also plays an important role in the development of the interstellar medium, the vast expanse of gas and dust that exists between stars. The interstellar medium is not a uniform substance. It's made up of hot and cold regions, dense and diffuse areas, and regions that are rich in elements like carbon and oxygen. The dust in the interstellar medium helps shape this environment by influencing the cooling and heating processes that occur there. In some areas, the dust absorbs light from nearby stars and re-emits it in the infrared, which helps cool down the gas in these regions. In other areas, the dust can block light, allowing the gas to remain cool and conducive to star formation. The interplay between dust and the interstellar medium is also crucial for the formation of molecular clouds, which are the birthplaces of new stars. These clouds are made up of a mixture of gas and dust, and as the gas cools, it condenses into dense regions where stars can form. The dust in these clouds plays a key role in cooling the gas, allowing it to collapse under its own gravity and form new stars. Without dust, this cooling process would be much less efficient, and the formation of stars would be much slower. Even outside of star-forming regions, cosmic dust is everywhere in the universe, even in the distant reaches of galaxies. Some of the most distant galaxies we observe are full of cosmic dust, which can give us insights into the early universe. In these distant galaxies, the dust can obscure our view of the stars and galaxies themselves, but it can also provide us with valuable information about the composition and evolution of these galaxies. By studying the way that light passes through this dust, astronomers can learn about the chemical makeup of distant galaxies, including the presence of elements like carbon and oxygen, which are key to the formation of life. Interestingly, cosmic dust isn't always stationary. It can travel across vast distances in space, pushed by radiation from stars, supernovae, and even the gentle pressure exerted by light itself. This phenomenon is known as the radiation pressure effect, and it causes dust grains to move through space. This motion of dust is not random, though. It follows predictable patterns that are influenced by the forces acting on it. For example, dust in the vicinity of a hot star may be pushed outward by the intense radiation, while dust in a supernova remnant may be propelled outward by the shockwaves created by the explosion. The movement of cosmic dust is also influenced by the magnetic fields that permeate space. These fields can cause dust grains to align themselves along magnetic lines, affecting their movement through space. In some cases, magnetic fields can even cause dust to spiral around them, leading to the formation of cosmic structures like nebulae and accretion disks around black holes. This adds another layer of complexity to the cosmic dust cycle, as the magnetic fields of stars, galaxies, and other cosmic objects interact with the dust and help shape the evolution of these structures. As dust moves through space, it also interacts with the light emitted by stars and galaxies. Some of this light is absorbed by the dust, while other light is scattered, causing the light to change color. This scattering of light is why the sky appears blue to us here on Earth. It's caused by the scattering of sunlight by the particles in Earth's atmosphere. In space, a similar effect occurs when starlight or light from distant galaxies passes through clouds of dust, causing the light to be scattered and reddened. This is known as interstellar reddening, and it can give astronomers important clues about the composition and structure of the dust clouds in space. This process of scattering and absorption of light by dust also affects our observations of distant objects in space. In some cases, the light from a distant star or galaxy may be dimmed or altered by the dust along the way, making it more difficult for astronomers to observe these objects. However, in some cases, this dust can actually help us study these distant objects by acting as a natural filter that removes certain wavelengths of light, allowing us to study the remaining light in greater detail. Cosmic dust is also responsible for some of the most spectacular phenomena in the universe. One of the most stunning examples of this is the beautiful and mysterious nebulae, which are clouds of gas and dust illuminated by the light of nearby stars. These nebulae come in many shapes and colors, from the bright, colorful reflections of light in regions like the Orion Nebula to the dark, mysterious clouds of dust that obscure the light from distant stars. Nebulae are often the birthplaces of new stars and planets, and their intricate structures are shaped by the interplay between gas, dust, and the forces of gravity. Another striking example of the power of cosmic dust is the formation of comets. Comets are made of dust, gas, and ice, and they are often thought of as dirty snowballs that have been flung from the outer reaches of our solar system. When comets approach the Sun, the heat causes the ice in their cores to vaporize, releasing gas and dust into space. This creates the bright tails that we see when we observe comets from Earth. The dust in these tails is a direct product of the cosmic dust cycle, as it has traveled across vast distances through space, eventually becoming part of the comet's structure. In the distant future, the cosmic dust cycle will continue to unfold, shaping the evolution of stars, planets, and galaxies. The dust we see today is part of a long, ongoing process that has been happening for billions of years and will continue for billions more. As new stars are born and old ones die, the cycle of creation and destruction will continue, with cosmic dust playing a crucial role in the shaping of the universe. This dynamic, ever-changing process ensures that the universe will never be static. As long as dust continues to cycle through space, it will remain a fundamental part of the ongoing evolution of the cosmos, constantly contributing to the birth and death of stars, planets, and galaxies, and ensuring that the universe remains a place of constant change, growth, and transformation. As cosmic dust cycles through space, it becomes clear that this seemingly small and invisible matter has a profound influence on the universe at large. The subtle and often overlooked role of cosmic dust in the formation of stars and planets also plays a crucial part in the way galaxies evolve over time. In fact, the presence of dust in galaxies is what helps astronomers understand the formation, age, and makeup of galaxies themselves. One of the key ways in which cosmic dust contributes to galaxy evolution is through its effect on star formation. Dust particles in molecular clouds provide an essential function by promoting cooling in these dense, cold clouds of gas. Without the presence of dust, the gas in these clouds would remain too hot to condense and form new stars. In many ways, cosmic dust acts as the catalyst for star formation by lowering the temperature in these regions, allowing gravity to take hold and collapse the gas into dense regions where stars are born. Without this cooling mechanism, stars would be far less abundant, and galaxies would look very different. The presence of dust allows the universe to continue its cycle of star creation. Stars give rise to new elements and dust, and as these stars eventually die, they release their matter back into the cosmos, continuing the cycle. Some of this material is then used to form new stars, while other elements remain as dust, serving as the building blocks for the next generation of celestial objects. In addition to its role in star formation, cosmic dust also plays a key part in the chemical makeup of the universe. The elements found in dust grains, such as carbon, oxygen, and silicon, are the very building blocks of life. When dust is incorporated into new stars and planets, these elements become available for the development of complex molecules. In this way, cosmic dust helps foster the conditions necessary for life as we know it. It's easy to overlook the importance of cosmic dust because it's so tiny and difficult to observe directly. But thanks to modern technology, astronomers are able to study the effects of dust in greater detail than ever before. Instruments like the Hubble Space Telescope and the ATACMS Large Millimeter/Submillimeter Array, ALMA, allow scientists to peer through dusty regions of space and observe the processes taking place within them. For instance, ALMA has provided us with detailed images of distant galaxies, revealing the abundance of dust in these galaxies and helping scientists understand how galaxies evolve over time. In these observations, we can see how dust interacts with light, obscuring our view of stars but also allowing us to study the gases that are present in these distant galaxies. The ability to study cosmic dust through these advanced telescopes has opened up a new window into the complex processes that govern the universe. Another significant aspect of cosmic dust is its role in shaping the appearance of the universe. Dust, by blocking and scattering light, has a profound effect on the way we observe the cosmos. When light passes through interstellar dust, it is scattered, which can lead to the phenomenon of interstellar reddening. This effect causes distant stars and galaxies to appear redder than they actually are. In essence, cosmic dust acts as a filter, altering the light from these objects and making them appear different than they would if no dust were present. In addition to affecting the light that reaches our telescopes, dust can also change the appearance of entire nebulae. For example, dark nebulae, large clouds of gas and dust that block the light of stars behind them, are often seen as dark patches against the backdrop of the brighter regions of space. These nebulae are home to the cold, dense regions where stars are born, and their dark, silhouetted appearance is a direct result of the dust they contain. One particularly interesting aspect of the relationship between cosmic dust and light is the role that dust plays in shaping the formation of galaxies. The density of dust in a galaxy can influence how it behaves. In some galaxies, a higher concentration of dust can lead to more efficient cooling, which can enhance star formation. In others, dust may be less abundant, leading to slower star formation and less overall activity. The amount of dust in a galaxy can also influence its appearance, as dust clouds can block light from the galaxy's stars and gas, giving the galaxy a darker, more opaque appearance. In addition to its effects on galaxies, cosmic dust has profound consequences for the broader environment of space. Dust plays a critical role in the process of accretion, the buildup of matter that forms celestial bodies like stars, planets, and even black holes. As cosmic dust accumulates in a region of space, it can form dense clumps, which then collapse under the force of gravity. This collapse is what drives the formation of stars and planets. In the case of planet formation, dust is essential for the initial stages. Small dust particles collide and stick together, forming larger particles. Over time, these larger particles collide and merge, eventually forming planetesimals, building blocks of planets. As planetesimals continue to collide and grow, they eventually form planets. Dust, in this sense, is the starting material from which entire worlds are born. The role of dust in planet formation is not limited to our own solar system. Observations of distant exoplanetary systems have revealed that dust plays a crucial part in their formation as well. By studying the dust around young stars, astronomers can learn about the early stages of planet formation and get a glimpse of how planets might form in distant systems. This research is particularly important because it could provide insights into the formation of habitable planets, which may be necessary for the existence of life beyond our own solar system. As we consider the life cycle of cosmic dust, it's also essential to understand its impact on the environment of our own planet. While we're often shielded from cosmic dust by Earth's atmosphere, some dust still manages to make its way to the surface. In fact, it's estimated that approximately 40,000 tons of cosmic dust fall to Earth every year. This dust plays a role in the Earth's environment in a number of ways, some of which are still not fully understood. For example, the dust that falls to Earth can influence the climate. When it enters the atmosphere, it can reflect sunlight, cooling the Earth's surface. This effect is similar to the cooling influence of volcanic eruptions, which can release particles into the atmosphere that block sunlight. Cosmic dust also carries trace elements like iron and silicon, which can be deposited in the ocean and contribute to the growth of phytoplankton, tiny organisms that play a key role in the Earth's carbon cycle. Furthermore, cosmic dust can be used to study the history of our planet and the universe. By analyzing the composition of dust particles that fall to Earth, scientists can learn about the types of stars that created the dust, the conditions in the early solar system, and the processes that shaped the Earth's environment. This research allows us to connect the dots between the dust we see falling to Earth and the broader processes that govern the universe. On a grander scale, cosmic dust helps us understand the intricate web of interstellar connections that links everything in the universe. It reminds us that the universe is a complex, interconnected system where even the smallest particles play a vital role in shaping the cosmos. Cosmic dust isn't just something we look through. It's something we look at to better understand the universe itself. The cosmic dust cycle is an ongoing, dynamic process that touches every aspect of the universe. It's an integral part of the life cycle of stars, galaxies, and planets. And perhaps most intriguingly, it's part of a larger, ever-evolving system of recycling matter in the universe. The same dust that once formed our Sun, planets, and Earth continues to move and interact with the cosmos, participating in the creation of new stars, new planets, and new forms of life. In a way, the cosmic dust cycle is a reminder of the universe's incredible complexity, and the unending cycles of creation and destruction that govern the cosmos. It shows us that even the tiniest particles, invisible to the naked eye, can have an immense and lasting impact on the universe. Cosmic dust, in all its forms, is a fundamental part of the grand story of the universe. A story that is still unfolding, as dust continues to be recycled in the vast expanse of space. The journey of cosmic dust is far from being a simple one. It's a tale of constant transformation, where the tiniest particles become integral components of grand cosmic structures. As we move forward, we can see how this cycle continues to shape the universe. One of the fascinating aspects of cosmic dust is its interaction with the light from stars. When light passes through cosmic dust, it undergoes a transformation. Light is scattered, absorbed, and sometimes even re-emitted by dust grains. This phenomenon, known as extinction, causes distant objects to appear dimmer than they really are. It also shifts the light's color toward the red end of the spectrum, a process called reddening. Through this interaction, cosmic dust alters the way we perceive the universe, creating a cosmic veil that challenges our observations and requires innovative techniques to peer through. This ability of dust to scatter and absorb light also has another important consequence. It allows us to study the physical properties of distant stars, galaxies, and nebulae. By observing how light is affected as it travels through space and interacts with dust, astronomers can uncover vital information about the density, composition, and temperature of these distant objects. This can give us a deeper understanding of how galaxies form, evolve, and interact with their surroundings. However, the impact of cosmic dust doesn't stop at scattering light. Dust also contributes to the formation of complex molecules and organic compounds, playing a crucial role in the very chemistry of life. These dust particles, made up of elements like carbon, oxygen, and silicon, can combine with other molecules in space to form complex organic compounds. These compounds might not only contribute to the birth of stars and planets, but also potentially create the building blocks for life itself. The discovery of complex molecules in interstellar space, such as amino acids, has led to the fascinating possibility that the ingredients for life may exist elsewhere in the cosmos, carried by cosmic dust to other planets. It's worth noting that the formation of complex molecules on dust grains is a highly intricate process. In cold molecular clouds, cosmic dust acts as a catalyst, allowing chemical reactions to occur on its surface. These reactions can lead to the creation of new, more complex molecules, including those that are the precursors to life as we know it. For example, dust particles in molecular clouds could serve as the sites for the formation of prebiotic molecules, which might be transported to planets during the early stages of star and planet formation. As cosmic dust travels through space, it also has an important role in determining the types of environments that will eventually be conducive to the formation of habitable planets. Through its presence in star-forming regions, dust helps regulate the cooling and contraction of molecular clouds, enabling the birth of new stars and planetary systems. Additionally, by contributing to the chemical enrichment of young stars, dust influences the composition of planets that form around these stars. The materials present in dust grains become integral components of these planets, which can ultimately lead to the development of atmospheres, oceans, and possibly the conditions necessary for life. One of the major ways that dust contributes to the formation of habitable environments is by enriching planetary atmospheres. As dust grains collide and stick together, they release gases into the surrounding space. These gases, such as water vapor, carbon dioxide, and nitrogen, are essential for the creation of stable atmospheres on planets. Without the influence of cosmic dust, the building blocks of life, water, organic molecules, and other crucial compounds, might not be available in the quantities needed to sustain life. In this way, cosmic dust plays a foundational role in shaping the very environments that could give rise to life. The effects of cosmic dust can also be seen on a larger scale when we consider the birth of stars and galaxies. In the early stages of galaxy formation, dust acts as a cooling agent, allowing the gas and dust within a galaxy to condense and form new stars. Over time, as stars continue to form and evolve, they generate heavy elements like iron, carbon, and oxygen, which are then incorporated into the surrounding dust. This process, known as nucleosynthesis, leads to the formation of a complex mixture of dust that becomes the raw material for future stars and planets. As galaxies continue to evolve, cosmic dust undergoes a series of transformations. Dust can be swept up in supernova explosions, expelled from dying stars, and incorporated into new generations of stars and planets. Through these processes, dust is continually recycled, helping to drive the cycle of star and planet formation. The composition of dust changes over time as it interacts with different regions of space, allowing for the creation of new, more complex molecules that can further enrich the material available for future generations of stars and planets. The study of cosmic dust also provides insights into the life cycle of stars. When stars die, they often expel large amounts of gas and dust into space. This material can be enriched with heavier elements created during the star's lifetime. When a star explodes as a supernova or sheds its outer layers as a red giant, it releases these elements into the surrounding environment. The dust created by these processes is then incorporated into the next generation of stars and planets, completing the cycle of life, death, and rebirth in the universe. As we explore the cycle of cosmic dust, we must also consider the future of this material. The dust that exists in space today will eventually become part of future stars, planets, and possibly even new forms of life. Cosmic dust's role in the universe is cyclical, with each generation of stars and planets contributing to the next. Just as the elements found in cosmic dust have their origins in the cores of stars, they will continue to be recycled into new stars and planetary systems. In the far future, the distribution of cosmic dust will continue to evolve as the universe itself expands. As galaxies move farther apart and stars burn out, the amount of dust in the universe will gradually decrease. However, cosmic dust will always play a role in shaping the universe, no matter how distant the future may seem. The cycle of dust and matter will persist, continuing to influence the formation of stars, planets, and galaxies long into the future. In conclusion, the cosmic dust cycle is a key component of the universe's grand design. Dust, often invisible to the naked eye, serves as the raw material from which stars, planets, and possibly even life itself are created. Through its role in star and planet formation, as well as in the chemical enrichment of the universe, cosmic dust is integral to the processes that shape the cosmos. While often overlooked, this seemingly insignificant matter plays a central role in the ongoing evolution of the universe. From the birth of stars to the creation of planets and the potential for life, cosmic dust is deeply intertwined with the fabric of the cosmos. As we continue to explore the mysteries of the universe, understanding the role of dust helps us unlock the secrets of star formation, planetary systems, and the origins of life. Cosmic dust may be small, but its impact is immeasurable, influencing everything from the creation of galaxies to the development of habitable environments in far-off worlds. It is a testament to the interconnectedness of the universe, where even the tiniest particles have a part to play in the grand cycle of cosmic creation and destruction. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.